what this is all about. So we were asked to teach environmental simulations to this amazing bunch of students. And well, Aris and Sarah, I worked with them in the past. So Sarah more, we were like together in the Bartlett, and also a few other opportunities since then. And Aris, who I've met more recently, but like they're both like really great in what they've done. I have done very little in this course, so I give all the credits to Aris and Sarah because they've been doing the teaching in this course, and I'm really, I have to say thank you to both of them. I'd like you to say a couple of words in a minute, because they focused, and that was like the kind of like the principle, because they focused more on the actual kind of like let's say theory and research behind it, rather than just, you know, simulations and tools. So these students came not having any kind of like exposure to environmental simulations before, maybe like some very kind of like coarse one, and within like a couple or 3 months they managed to you know, not just run simulations and, you know, use ladybug tools or like, you know, have you energy simulations, but actually understand them and use them for design. That's kind of like what I think is the most important achievement. And I would like to ask the faculty as well to focus on that, on the actual, like, you know, questions, research questions and answers through simulations. Sarah and Aris, please introduce yourselves and share a couple of words, and then I will introduce the jury. Sarah, we start with you.
All right. It's great to see everyone. It was a pleasure teaching this class with Angelos and Aris. I am currently a PhD student at MIT, doing a PhD in building technology. And previously I was working, I was leading some research into computation and environmental performance at KPF. And I'm extremely excited to have you all here, and I really want to see what you've all come up with, and I'm sure it's going to be exciting work. And yeah, I'm leaving floor to Aris.
Hi from me also. I'm Aris Bartholomeos. I'm a postdoctoral researcher at Aristotle University of Thessaloniki, and I also teach there on contract. I've been amazed by your progress. I've seen from the beginning of this course up until the end on how you actually used your newfound knowledge to integrate all those things you learned in this course in your own you know, design workflows. And I'm very eager to see the fruits of your labor right after this short introduction.
Thank you, Aris. So yeah, with not any further ado, I will introduce the jury in the order that I see them now. I hope you can all hear me because my connection is slightly unstable. Yeah. First one is Theodore Galanos. Theodore Galanos is a researcher, and I think I'm losing all of it. Can you still hear me or not?
Yeah.
Okay, perfect.
Yes.
So Theodore Galanos is a researcher and longtime collaborator for the City Intelligence Lab, and the, let's say, the mind behind the artificial intelligence endeavors we've done recently, which is called Infrared, the Intelligent Framework for Resilient Design. Works a lot with machine learning, of course, has worked a lot with environmental simulations in the past. And he's also kind of like co-developed the butterfly tool with Mustafa in Ladybug. I think most of you know already Theodore. Emanuele, professor in Parma and KADK, has worked a lot on kind of like environmental simulation and regenerative processes for urban design. Yeah, there's an adjustment to the groups, okay. Then Matilde Marengo, head of studies still in IAC, yeah. This title changes and I don't follow always, but I think I'm correct in that. Head of studies in IAC. She was also co-supervisor of my PhD, so I'm glad we have you here. And Yeah, she's done a lot of work in research and theory in IAC, teaching students for quite some time now. I don't know how many years are you in IAC already now? Is it 10 or so?
8.
8, you're getting there. And Teresa Fink, who is a research engineer in IIT, in the same company that I am in, and she is probably the key person in IIT's digital resilience cities in running environmental simulations and using them for design. So very much into kind of like the kind of like true use of these tools in design. I can't see. 1 second. We are missing. Okay, Eduardo is here. My order has gone all weird. Yeah, Eduardo Rico.
We are too many to fit on one screen.
Yes, civil engineer and researcher in the Space Syntax group, and also the co-director of the Landscape Urbanism Master in Architecture Association. So nice to meet you, Eduardo, and great to have all of you here. So let's start, or is the first group ready? Should we start? Yeah?
Yeah.
Okay, so group 1 should be, the first group should be
group number 7.
Group number 7 is ready to present. So a little bit of a kind of like, before you start, a little bit like of advice to the jury. So the structure is like 7 minutes presentations, and we're trying to keep it very, very short, and then about 15 minutes of comments. Try to keep your comments relatively short. So no more waiting. First group, you go.
I will give you the 2 minutes warning, okay?
Okay.
Thank you.
Great.
Okay. Hi, so we are team 7, Kim and Jaime, and we are going to present the environmental analysis that we have done for designing a public center in Madrid. This is our site, which is located in the city center of Madrid between La Latina and Lavapiés neighborhoods. And as we already know, Madrid, as every other big city, has a problem with the heat islands and the fact that they produce increasing temperatures. So foremost, this is something to be considered for our analysis and our design. We started doing a climatic analysis, and we could see that there is a really hot and dry summer and a slightly cold but quite humid winter. We also did some comfort analysis, which showed us that during all seasons, there are some comfort days, being summer the one which has most of them. But we saw that it would be really important to have a cooling system during the season. With the radiation analysis, we saw that there is a quite proportional high radiation distribution on all our sites, with the left below bottom corner, which receives a bit less of radiation. And that radiation comes mostly from direct radiation, as the site is facing southeast. Through this environmental analysis, we understood that our site receives a high radiation, especially on the upper corner, and that radiation is an important factor to be considered in our design. That's why we asked ourselves how the solar analysis can define architectural building and facade design, and also interior comfort within other key factors of conception. To be able to answer this question and how we optimize our project, we used several tools. We started with PetSim, Ladybug and Honeybee, and Pachyderm or Snail for the analysis. But then we continue using Ladybug for optimizing radiation through Wallasey. And at the very end, also Ladybug and Honeybee for the facade design for daylight and energy consumption analysis, and also as decision makers. So as we have seen, mainly the environmental problematic that we have to face is the high radiation and high temperatures, and dry weather in summer, which we take as input parameters for our project, with sun direction, radiation, or building orientation. Then before the design and optimization phase, we did some initial mass studies through radiation and also energy consumption. And we saw that due to the shading that one building could produce onto another, we didn't have such big values of cooling load.
So I'm going to present optimization and our strategy to combine data. So this is we tested several optimizations. So this is our final optimization based on our context and site analysis. We did our goal was to optimize the model with a maximized floor and then maximize the floor and then minimize the radiation and other with other factors. So this is the result that we selected, which was on the average of a blank for all the fitness values. And this is how it looks like our final mass with circulation in the middle. But also there is a small building on the street block solar radiation for a big building inside. The strategy for our facade design is that we use insolation analysis and acoustic ray tracing data, but also we gave openings by different percentages, depends on programs. In order to explain our methodology to integrate over all output data for facade design, we explain with the case of the building A. With the triangle mesh model that is also used for the solar radiation analysis, is tested to find out the radiation threshold for opening. And then we got a threshold of 60% of facade where it's received mid and high radiation, and 40% for mid-low radiation area. Then the second variation for opening and closed panel is related with program and its privacy. As you can see, two images of blue and gray. As the percent value is increased, more windows are creating. For example, for closed panels, the higher percent we have, the less number of closed panels for the ground and first floor, where are the public space. So for the sound, we also use the radiation meshes. So the value is as the value is increasing, the range of the attractive point is increased. So we usually in the end 10% for the plants with the extruded panel. So again, for the area where it has a high solar radiation, we're using it to close the panel, and mid and low radiation we use we had an opening. So this is the reference for the panel systems. So this is the combination of our design. So the yellow, light yellow is upper area, and dark yellow is like is a ground and first floor. So we gave 20% for upper floors and 80% for down floors. And then we increased the value to test, and also our proposition.
Time, so try to finish as quick as possible.
Nice. Yeah, so and then our question is, how can you prove to a client that which design is better? So if we propose to we did daylight availability study. This is our decision maker for which is for our final design. For position 1 is better because according to an annual sunlight exposure analysis, we have a very lower value for the for position 1. So which means there is less potential glare and overheating from daylight. And also we did energy consumption test, but total cooling and heating load is cooling load is less than proposition 2. So this is better than this one, but the total heating load is higher than proposition 2. So this is a little problematic in the end. So we have to tested our openings, and yeah, so during the summer they have quite good daylight value. So this is the final view. Unfortunately, we have a technical problem this morning, so the video hasn't finished yet. Yeah, thank you.
Thank you. So, comments from the jury. Where do we start? Just, I can't see raised hands and things like that, but we can see the video actually, but not the environmental one. Comments from the jury. You don't want me to pick names, so maybe you start. No one? Theodore, any comments?
Yeah. So yeah, I was just waiting to see if anyone. So thank you for the presentation. It's really great, and I like the fact that you chose sort of orthogonal metrics. So it was like I think a good choice to choose like metrics that kind of compete with each other in a way to get like. And I was wondering, like when I see the multi-objective optimization, I always think that this is sort of the limit. Like there is 3, you can't really add more metrics. There is actually a whole field called many objective optimization that says we do 3 and more, right? So I was thinking, like, did you come across this difficulty, or how would you think you would integrate more metrics into your design? I know that you chose a design and then you assessed it as convincing to the client, but did you have any thoughts of how to try to integrate more metrics in some way, or maybe in the optimization, I mean, somehow, maybe like combining?
We wanted also to test thermal comfort, because the public space, outdoor thermal comfort, I mean, because the public space was important to us, and see how the terraces could be defined and so on. But yes, you say there were too many variables if we include that.
It was interesting for us that, like you said, we tested for optimization. We tested really few rules, like 2 or 3 to like dividing or like minimum solarization, and then after 2 or 3 times optimization, like we have more rules to have a more specific design. So it was very interesting. So like Jaime said, if we have more time, we will have more, like, I think we can have more specific design with more rules.
Thank you.
Perhaps I have a question.
Right.
Well, first of all, congratulations for your achievement in such a short time, and there is a high complexity of analysis, which is remarkable. I have a question for you. Do you think there can be any weaknesses in addressing different analysis at different scales? In concept design, you have performed certain analysis. In preliminary, once you have chosen your massing, you have performed others. And then when you approach detailed design, perhaps you introduce biophilic design as well as daylighting consideration. Do you foresee any risk in to have this scale-based type of analysis? Do you think it's also possible to include a more wide set of analysis since the early stages?
So your question is like since an early stage of conception, we do like
I can try to help. For instance, running a daylighting analysis at the later stages can be in contact with some of the target that you develop in your massing, that perhaps is purely energy driven.
Well,
so
when we had an objective very first time, like we had a lot of goals, of course, including with environmental conditions like good comfort, physical comfort, and inside and outside. But like we had too many conditions, so it was hard to mixing everything in one bowl. So and then also computer has a really like very slow with a lot of conditions. So we simplify it the very first time, and in the end, that's why we choose the Ladybug tools to prove our design, and then after that we have to go back to the first stage and then change the values and then retest. I think you are right. It's be better like we can since very early stage, if we can compact everything, I think it will be more effective. But I don't know, it was really.
And I think that it would have been really good if we could have included that daylight analysis, for example, because of course one building is affecting the daylight availability onto the other as they are close and they are one in front of the other. So maybe in the optimization, and that could have been another parameter, like as closer as they are, then the less daylight that the back building would be receiving on the ground floor and so on. But yeah.
I think a principal reason we didn't try was we tried one time and then Ladybug need a lot of honeybee need a lot of calculation. So every time we changing it and then we forgot to turn off the toggle and then rerun and then okay, we just stopped and then we simplified our rules and then.
Sure. I mean, beside the technicalities of the simulation, there are probably different approaches. One is to have 2 or 3 key values that go through all the project, and the other is to introduce new values at different stages. So it's not a critique; it's just to understand what was your thinking behind. Thank you so much.
Yeah, thank you.
Yeah, maybe if I can continue on that, coming from a less obviously technical perspective. I think congrats guys. I think you've been really rigorous in the development of the project. In relation to what Emanuele was saying now, to add more parameters, I think it might be interesting to critically reflect on what comes out of the simulations, and you know, knowing what your target issue is, which is the heat island effect, what other kind of elements you could integrate potentially into the built environment to sort of tackle those issues. So for example, I saw that in the render, you do have elements of vegetation. It might be interesting also to look at how you could play with that to deal with some of the comfort issues. So maybe integrate vegetation, or I know that, for example, Patrick Blanc has done several green wall systems in Madrid. So how that could allow potentially the building to perform in relation to comfort, but also heat, reducing the heat island effect in the city, in the public space, sorry. And I was also thinking that it might be interesting to look at, you know, like what shape the building has come out. So you have a flat roof, and you were talking about the potential of sort of integrating energy capture or in some way storing energy. So it might be interesting to reflect on how you can integrate also their other elements. And maybe, you know, also thinking about how you were talking about the client and which sort of building is more ideal. Thinking about what parameters the client is after, so potentially maximizing sort of the surface or the ground surface available within the building, and how can you compensate if you maximize the ground surface, for example, how can you compensate potentially with other elements such as vegetation or canopies of some sort within the environment. And I was thinking that it might be interesting for you guys to check out the building by Jean Nouvel in Sydney called Central Park 1. And it's actually a collaboration between Jean Nouvel and Patrick Blanc. And so they integrate a series of other elements within this kind of high-rise building to be able to ensure sort of thermal comfort and reducing the heat island effect within the built environment, but also ensuring that like the light arrives at all of the different floors. And then finally, I would say, you know, like the last thing is it would be interesting to reflect on the materiality of the building and how this too can allow you to engage with this idea of sort of like optimizing the performance of the building itself. And so adding in, as Emanuele was saying, some other parameters as you go on or go forwards in the design. And I invite you guys to do that even if the course is over, because of course, this is always an interesting opportunity. So thanks, guys.
Yeah, thank you.
Thank you.
Yes. Also, my side, congratulations for a really nice presentation. I enjoyed it a lot. And what I think is really interesting, the transition that you actually started with the boundary conditions on like a zoom level of the solar radiation. Then you brought it to the next step of the massing by building up the concept, which is based on the boundary conditions, and then having different impact factors. So you actually did the transition from like starting with the solar radiation back to actually, or like front to the solar radiation on the facade, that you split the different thresholds, like where it's open, where it's closed. So you actually brought the level of detail of your simulation in a really nice way into your design. Plus the storyline, like how you presented to the client, that you actually come from the very start to explain it in a way that they actually understand and perceive your simulation results in a way how it is beneficial for them, plus also beneficial for the people that would actually use this space. What I think would be important if you bring it to the next stage, if you want to sell to your client also the economic impact, because all those massing studies, of course, if you have a lot of overhang, they will go into structural design, they will make it more expensive. So this is now for environmental performance, it's the best solution. But if you would bring in structural engineering economic impact for the client in the end, that will also affect and change. Plus, if you go for the solar radiation on the facade and bring it into conclusion that the openness and closeness of the facade panels, if you bring, as suggested, the vegetation in the panels itself, the maintenance issue of this vegetation in the facade will also bring in another factor for the economic impact of the building. So if you want to like sell it as a whole holistic design, of course, it's good and really important that it's environmental driven from the very beginning, but also consider those questions from the client once you want to sell it to them, that they will bring in, okay, now I can reach more GFA, but if there would be less overhang, they would have less shading, but maybe it's just a public space down there, and just like also to bring this negotiation process in the direction that you can have different impacts of those metrics as well from economic and structural side.
Thank you, Teresa. Eduardo.
Thank you. Thanks for the presentation. I think you've made a huge effort, and it's really, really stunning what you have achieved in this period of time. My only comment would be somehow some of your results appear too suddenly for a potential client. I think you've made the right question when you were asking how can we actually communicate and sell this better to the client. And obviously, you have to mature all these things to be able to do it in the future. But it would be good if you think about mapping or projecting the results you're obtaining towards ideas he or she may have in the back of her mind or his mind when looking at the project. So using precedents, typologies, which in a way make it easy to relate and to understand why did you took which decision. Because somehow it is too sudden if you think about it from obviously an external perspective. that's an exercise that can be done from the ML or AI point of view. So you can, and there are techniques to actually carry that work out and help you do that. But if obviously that would take more time, but in other cases, you would have to make the effort yourselves to, in a way, explain why some of these decisions have taken place. Why did you get the diagonal? Why did you actually climb up backwards? I mean, there are all these reasons that you took for a very good reason. So all these decisions you took for a very good reason that suddenly appear too suddenly. And the same applies for some of the later optimizations with Wallasey. I believe there are methods of expressing and showing all the options and explaining why you choose what. And it's important to be able to do that job as well. But other than that, you've done a great work. Great.
Thank you. Thank you, Eduardo. And any last comments from the students or from Aris and Sarah before we proceed to the next group? Okay, we can go to the next one then.
Thank
Group,
you very much.
Thank you for the presentation and for the effort, most importantly. Group 2 is presenting next.
Yep.
Can everyone see the screen?
Yes.
Just a second. Okay. Okay. Good day to everyone here. We are group 2. Myself, Amar, Marissa, and Pedro. Our site is located in Ubud, central Bali, contrasting to the coastal settlements of Bali. Ubud has a cooler climate and a much more dense forestry. Generally, it's a warm and humid climate. Being located near the equator, Bali has a warm tropical climate with a year-round temperatures averaging 27 degrees Celsius with a humidity level of about 85 to 90%. There are 2 seasons in Bali, the dry season between the months of May and September, and the wet season between the months of October to April. We can see here that the driest months are also the coolest months. Between January and March, winds coming from the west are powerful and gusty, whereas in the months between June and September, the winds flowing from the east are very consistent but not strong. Hence, this is also the kite flying season in Bali. The difference in total radiation levels does not change much between the 2 seasons. The radiation levels remain consistent, but in high levels. Naturally, there is more diffused radiation in the wet season than the dry season. Similarly, the vertical angle of the sun does not change much between the wet and dry months. As we see here, the sun is mostly overhead all year round. And the site we've chosen is surrounded by mainly small 1, 2, or 3-story buildings. Hence, there is no direct obstruction to the radiation to the site. So in conclusion, we can say that there is a high solar radiation all year round, so proper shading should be provided. Monsoon season is extremely high in humidity, which creates discomfort, especially when temperatures are also very high. There is a good amount of wind all year round, so it should be utilized for natural ventilation and stack effect.
We started then with the research question. Can we create opportunities from the climate by harvesting solar and wind energy from the environment, decreasing and reliance on energy produced by fossil fuel, and at the same time create indoor and outdoor space that is comfortable? Our objectives and methods are self-shading and building the building to reduce the heat inside the building, create openings that allow cross ventilation, determine how much solar energy can be harvested, and creating comfortable outdoor spaces, sheltering from rain, wind, and sun. We started with a quick tests at the beginning of the course to see the position of the building and how the building affects the site, or how the site affects the building, and regarding total radiation and the different levels. With the different levels of radiation, and since there is no obstruction from the sun path on the site, we concluded that it does not affect the total radiation. The second test, which you can see more on the right, we started with a larger roof that can increase the solar radiation on top to harvest the sun energy, but also use this staggered volumes to act as a self-shading device. Both worked well, so we decided to move with our final geometry concept. We derived this geometry from Wallasey, giving 3 parameters. First, the maximizing solar radiation on the upper surface to position solar panels. Second, to maximize shading or self-shading. And third, to maintain a geometry of the volume.
So then we went on to test different massing surfaces. And here we ask ourselves like 2 different questions. Can we optimize the mass for solar radiation without compromising the bamboo related design? Because that is a material that we are going to use in this project based in Bali. And how much energy can that provide to the building? So we went to 3 steps from the first test of Wallasey to the second test of Wallasey that gave us this edged geometry, and then to the third one, which we then smoothened out to be able to use bamboo construction and suitable for bamboo construction. And when we look at the numbers here and looking at other drivers of our project, which is the bamboo construction, the numbers don't differ too much from Wallasey 1 to the smooth Wallasey 2. So we decided to have this sustainable material and to go on with this value of total radiation that we could achieve with Wallasey number 2. And then we started to look at the efficiency of a solar panel, which is 15 to 22% that we can have now. And here we've looked at where radiation is the most on the top module, and calculated the 20% rate, and that is the rate that we've got. And then we looked at it from top, and now we're looking at it from the bottom, which is mainly low insulation. And here we see that there's opportunities to create the openings for entry and for operable for windows. And that's how we derive where the location of openings are. And then we looked at the skin design and these scales that we have on the building, testing different rotations and see what can, if we cannot increase it even more. So first one on top is just the surface. Second one is a random rotation of the skin, the scales, and the third one is based on where the high insulation and low insulation is, and we can see that it's slightly increasing. So in the end, we went from this flat building skin to something that is angled for optimal insulation and also to create these openings. And we have achieved increased insulation. And then we also looked at daylight autonomy and how when we rotate the skin at 0 to 45, which is what we have here, we can get enough daylighting, and we can even run the test again for 0 to 90 degrees and to create bigger opening. And then we had a look at the cross ventilation. The south side of the building, the site has no adjacent building, so it gives a big amount of wind flow. And so that is a potential for cross ventilation. Whereas the north side that has 2 to 3 story buildings are protected quite considerably. On the eastern and western side, based on the climate analysis that Amar just was talking about, the gusty winds from the western side is slightly protected by the low neighboring building. So even though we want the wind flow, but we do not want the wind flow that is gusty from January to March. So that's something that we have to bear in mind. There is consistent wind on the eastern side as it is next to an open space. So extra openings are also possible here. And then we looked at aggregating. The intention of this aggregation is to create a courtyard that can be shared by these 3 buildings. So aggregation 1, we managed to create a small courtyard of comfortable wind speed. And then we tried aggregation 2, which has the module on the south side. So using the existing building to shield on the north and west side. And aggregation 2 clearly provides a bigger area of comfortable wind flow in the courtyard area. And this is a simulation 6 a.m. to 8 p.m. on 2 days of winter and summer solstice. And by organizing our building aggregations in a certain way, we can create this shielded, comfortable area. And then the solar adjusted temperature, the MRT, sun exposed versus sun shaded, obviously in a tropical country, sun exposed will be unbearable in the midday. And so we needed a strategy for the shading. And so we looked at shadow studies, important times of the day, 8 a.m. to 6 p.m. on summer and winter solstice, and determine where we need to shade the area, which is in red. And by doing the thermal comfort analysis of the average week of the year, we can see that it is confirmed that we do need to really well shade this courtyard that we want to create comfortable open space. And so our strategy for that is a very simple strategy, which is landscaping strategy, by using big tropical trees such as the banyan tree, and also in the areas where we need the most shading, and some other smaller canopy trees in the areas. Yeah, and what do you want to talk about this one?
Yep, and I think another consideration that we haven't really elaborated on was also the natural ventilation. So I think the form of our building is also well suited for stack effect to further enhance the natural ventilation within our building. So this section also shows how that sort of works within our building. And I think, and that's the end of our presentation. Thank you.
And I just like to add a little bit to what Amar just said. I think based off of like a lot of our comments with the tutors, that this strategy of solar radiation will create a lot of heat, and it's only natural that we use it again to create that airflow across the building. So this is why we have this last slide to remind us that absorbing solar energy will also create heat, and we will have to find a way to solve that problem. Yeah, I think that's all.
Thank you, guys. I think you have to stop here because you're a little bit over time. So let's go to the jury for comments. Very briefly, it has to be a little bit briefer than before because the presentation ran over a little bit. Matilda, do you want to start? I have you first in the order, or anybody else, actually, it doesn't matter, don't worry.
I just had 2 points of reflection. Again, I'm probably the least technical jury here. So one of the things is actually something that I have from my experience in Indonesia, and it's related to the luminosity. So I know that in tropical climates, the light quality or the quality of light that you have is very different, for example, with respect to what I was used to in Australia. And so I was wondering if that is something, I saw you did a daylight analysis, but by the design, which is very sheltering, I was wondering if you had taken into account the possibility to sort of analyze the quality of light within the building. And I say that also because at some point you say that you'd like to ensure, you want to decrease the energy use, but you want to ensure indoor and outdoor comfort. And you don't really define what are the exact parameters that your comfort is based on. And I think the usability of buildings or the luminosity is something that's really important. So maybe it would be interesting to sort of do a post-analysis on the built or the building that you do propose and understand how you could maybe then, you know, critically look at that and potentially optimize either by integrating sort of openings or panels that in some way move. I didn't really understand what the panels were, whether they're fixed or moving. But I think that's something that's important for the usability. I think the presentation was really complete and fantastic. And just about the comment that Marisa was saying at the end regarding the necessity to maybe cool, I thought it was very interesting how you guys are looking at the potential of sort of harvesting the rainwater within the building. And it might be interesting to look at how you can use that also as a cooling device to some extent at some periods of the year, you know, optimizing the ventilation and using that sort of water that or the rainwater that you're capturing to be able to enhance the performance of the building. So those would be my 2 comments. And maybe it's interesting, I mean, I had written down to look at the vernacular, the local vernacular, to maybe understand what are the building elements that are being used locally. I think you definitely went for a material that's being used locally, which is bamboo. But maybe also, you know, and this I guess is a general comment for everyone, when you contextualize your building, it's always interesting to critically reflect on what is being used locally or what is the traditional method of construction and how you can integrate that or the knowledge from that, the learnings from that into sort of this kind of, let's say, technological approach to the built environment. But thanks so much, guys.
Yeah, thanks, Matilda.
If I can quickly comment. First of all, thank you. It's an amazing project. It's very close to my heart and actually close to my home. So I will try to see if I can share something something that makes sense. And it's true that the tropics are a fascinating place. Like the climate does look a bit boring at first. Like it never changes. The diurnal temperatures are the same, solar as you very well described. But it's also, it can be unforgiving, but it also, I think it allows for a wide range of like solutions that can be, as Matilda said, either vernacular or natural based, let's say nature based. And in fact, the kampung houses, they do kind of do this, you know, like elevate everything. So you're away from the heat and leave natural ventilation everywhere. So I really like that you took these aspects into account. You had a very wide range of metrics, and I like that. I think they are needed in the tropics to understand performance. And one perhaps comment would be that I would like, and this is very personal preference, I know that a lot of people are focusing on renewable energies as the first thing or very high priority. I think in the tropics, they are much more interesting, but I would try to focus a bit more passive than active energy. So you did that in a sense through natural ventilation, through rainwater harvesting, and maybe, I'm not sure if stack ventilation is going to work, but natural ventilation is there. So I would, by focusing even more on this kind of aspects and not, let's say, PV as a major, let's say, metric, because it will push design towards something that it wants or the PV generation demands, right? You might find solutions that are more maybe viable in the local climate or context, because right now here, the buildings that are built to carry solar radiation are the very well-known boxes that we have, right? They have something on the roof. Yeah, but I really like the high porosity. I thought that the CFD is very important to do here, not because there are high winds, but because there are storm winds. So perhaps if you continue the study, you could conduct the studies just during those storm winds with those conditions, just to understand the climate vulnerability, because most of the other hours should be okay. And the last thing that I saw was, and I will stop talking, I'm sorry, is the rain. And the rain, as you may know, I'm sure you know, is a very big thing, is a very constant thing. And it's something to consider with this design. Natural ventilation is amazing here. It works very well, but also the rain, it's unwieldy. Like, it goes everywhere, right? So it's something to consider when implementing this.
Yep.
Thank you. It was very nice, very nicely done.
Thanks, Theodos.
Thank you.
again, quite good work, actually quite good and quite a lot. So I think you've managed to amass quite a lot of evidence. Just one detail, and coming from the landscape perspective, there is this moment where you place the 3 blocks one beside each other, and then suddenly 2 of them merge together in one slide. Hang on, how did that happen? And I think I would, and then afterwards you just put the trees and you sprinkle them around in a bit of a random manner. And I would have actually liked that you would have actually spent a bit of time on that side. So trying to introduce the vegetation and the building organization into the Wallaces and see a little simulation of how they self-organize and how do you actually fit them together to actually fabricate a proposal from the bottom up, from the landscape perspective. But I mean, that's actually asking just because I want to ask, and it's in my field, but otherwise I think you've done good work.
Okay, thank you.
So if I can build on that, I think I worked a lot into climate humid area with the Master of Extreme Environment we have in Copenhagen. And I have to agree with both Mathilde, Eduardo, and Theodore. I mean, planning vegetation and planning nature-based solution should begin at the start, or it should be relooked into the design process, because it can cause, as Angelos knows probably better than anyone else here, introducing vegetation layers means that we have to go and modify the scripts themselves, because the actual suite of Ladybug tools does not allow to consider, for instance, how, I don't know, rainwater collected change mean radiant temperatures. Of structure where perhaps water is channelized, as well as, of course, also all the latent here heat in atmosphere changes a lot, and surfaces of trees is different. So it's quite tricky, but perhaps is future steps to be taken into account.
Maybe I say here that because we were saying that yesterday also in the studio presentations, like, you know, we are asking the students that they have to like essentially like use, like, you know, as you say, put the vegetation as a design parameter in the beginning. But it's true that because of also the tools that we are teaching them not being there, it's also partly our fault. Like we didn't really focus as much on like vegetation, because there's like really not the tools there, which actually goes back to us, where we need to develop them.
There is the research project. There is the research project.
Exactly. But yeah, just wanted to say that. But yeah, I mean, I completely agree with all of you. I don't want to take the time. Teresa, it's your comment.
Thank you very much for the presentation. Really, really nice as well. What I really enjoyed is that you actually went into detail of building material on a contextual scale, but also on a sustainable concept overall for the building, not just considering like the impact of the environmental, like impact performance, like the solar radiation and the wind, but actually going in the building itself for like rainwater collection, how the facade, the panels are shaped in this direction, that you have the natural ventilation as a factor. And I think that's really important. Also, I think it's really good that you checked with different aggregation status, like how you place the buildings on the site, because this wind performance actually showed like just by having a really functional building environmental in itself, how you place it on the site and how they interact with each other is still an important factor. So it's really good that you also went for this step. Thank you.
Thank you.
Thanks, Teresa.
So thank you, everyone. Let's go to the next group, group number 3.
Yes, okay. We're ready. Let's be presenting.
Shoot. Try to keep this time.
Yeah. Can you see the screen?
Yes, we can.
Welcome, everybody. Our final presentation called Ubud 2. That is about creating cultural connections on a segregated city. This is a final presentation for the digital tools of environmental, and we're group number 3 is Andrea Kulukulak, Herman Bodenbender, and Sergei Krichkov. Our design is not based on the building, but it's based on a bridge that connects a segregated city. And we took the design drivers of using a sustainable material locally available in South Africa, prefabricated systems, and also use the disassemble and repurpose approach. Our site is located on the southern hemisphere on South Africa, in the city of Johannesburg, and more particularly on the CBD, that is a central business district. Something to notice about the CBD, that is in a segregated city due to apartheid, and also a particular site has a particularity that has been divided by a 75-year-old railway infrastructure, as you can see. As you can see on the right image, we got almost like a 30% open land, and that open land is not related to urban and green parks, but is related to how much the train occupies and creates, as you can see on the left image. Now we'll pass on to my colleague Andrew to talk about the weather analysis.
Thank you, Herman. So after we ran several analysis, we learned that the temperature is very comfortable, well, relatively comfortable in Johannesburg all year round, and the change is not too visible, too drastic throughout the year. I'd like to remind you that the summer is winter in Johannesburg and vice versa. So we also ran some humidity analysis, and we saw that it's comfortably dry. The most humid month, the wettest month is February, and we have a dry period from June to July. And we overall it's quite comfortable all year round, and the average yearly cool comfort factor is 0.417, which is very close to 0, being the optimal comfort. So it's on a more important note, solar radiation is a factor that we had to consider more, that you see in the next slide. Especially in the summer when radiation numbers reach up to 1,000 watts per square meters. Yeah, in the next slide you can see that we've done some macro analysis of solar radiation, and considering that our site is an open field of rails, it receives more than 13 hours of sun a day. Considering that there's no shade. And on the next slide you will see that we've done smaller analysis, microanalysis on the sites where the bridge touches the ground, and the south side is it's all open, no particular shade, so it receives a lot of sun radiation, whilst the north side is a little more protected by the surrounding 2-3 story buildings. We've also done the wind analysis that you'll see in the following graph. The wind is not too strong at any point during the year. The strongest wind reaches just over 10 meters per second, and it's coming from the north in October and September, and there's also some wind in the March from the east. I'll pass it back to Herman to talk about the design process.
So as a conclusion to the analysis, we then understood that both radiation and wind are factors that we need to use in order to consider it the way we design the bridge and how do we connect it. So we then started a design process. That is a bridge that connects a pedestrian bridge that connects north and south. And then what we did is we took all the selected sites and we identified the interstitial voids along the railways on which we can actually use to place our support. We then cast up grids of points, and then using a genetic optimization algorithm, we then started looking for the optimized path connection. We used 4 different goals. That the first goal is to be able to reduce the travel distance in order to create the quickest connection between A to B. And then goal 2 and 3, we started analyzing the both entry and exit slope in order to create a wheelchair and bike-friendly route. And also, 4th and most importantly, we also each iteration we measure the amount of radiation in order to try and choose the one that absorbs the least amount. This is then take us to a final solution. But the final solution, as you can see, we then did further analysis and testing on both sun hours and also radiation. And as we can see, and as we expected, we can see still a huge amount of radiation on the bridge that spans north and south. We got an average of up to 12 hours on the bridge. So now the question, so then we also further analyzed both on winter and summer. And as you can see in winter, our average of sun hours are decreased. But in summer, based on Johannesburg, at 1,600 meters above sea level, these values, this amount of hours and values for radiation are extremely harmful for the skin. So what we did is the question for us is how can we then create a pedestrian bridge that then grows a protective skin on the areas we want to host program. So this bridge hosts particular programs on the area highlighted there, as you can see on the top right image. So the question for us is how can we develop a parametric envelope that then reacts itself to the skin, to the sun angles, but also open himself to the views. So as you can see on the bottom left, that's the detailed design of this parametric scheme. And then in the image 02, you can see how from the southwest perspective, he opened himself, creating views towards the city. and a 0.3 closing self to actually stop the most strong sun. Then we did further testing and optimization, so we did it through a bunch of interactions for this scheme until we achieve the desired one that help us, as you can see here, on both winter and summer on this full day sequence to show us how actually after midday, they help us to protect on that highlighted area the people that sit and gather there. And also we did further both comfort. On the left is without the protective panel of skin into the structure, and the right side is with it. And I will pass it to my colleague Sergey.
Hi everyone, and as it has been already said, the predominant wind comes from the north, and this was kind of favorable for us in terms of the structural issues, because we basically have no lateral load in our bridge. However, we still have the comfort issues with the wind, where the bridge touches the ground. So we have concentrated on doing the CFD study on those two microsites on the north and south, and we have created a simplified model to test the CFD on it. And as you can see on the next slide, we have we have run the test and found out that the situation is actually not that bad. So the wind travels mostly along the streets, and the area where it touches the ground is kind of protected by the development next to it. And on the next slide, we'll see in more details how this has informed our design of these two ends, where the bridge actually becomes the building. Here you can see that the pressure of the wind that runs really along the slope. And on the next slide, there is, yes, this is a bigger scale simulation where we see the calm zone, and so we have located our leg wrapping around it so that we could create kind of a urban plaza next to it. And here it is with the actual bridge model. This is kind of the CFD study informed our local urban design where the bridge becomes a building. And a couple of more images of this parametric skin closing part of the bridge. But the location of the bridge, its orientation from north to south, which did help us in terms of wind, also makes it not exactly comfortable in terms of sun, because we can protect it only from the one side, which solves only part of the problem. And then for improving the situation, we planted a few trees in the middle of the bridge, but only in those spots where we have the lag, because obviously we can't plant the trees all along the span of the bridge. And well, with all the design constraints, that what we have arrived to, and now I'm passing it back to Herman to conclude the presentation.
And now we're just going to show a quick video that we just compiled. I want to share for optimized screen. Can you guys see the cover of the video?
Yes.
Perfect. And that's it. Thank you very much.
Well, thank you. So, jury. Eduardo.
Very good. I think it was super focused, super slick. And I guess there's a convincing final product that you present. And I think I would have 3 comments, like technical comments, technical critiques, which I think we can do because the results are clear enough to be able to do that. First of all is when you do the first, I think it's a Wallace that gets the line curvy doing that and finding the best solution. I think, and coming from a space syntax perspective, I think you should have actually included the larger scale context to see what's the best point of connection. The reason being is in the north side, your bridge seems to be pointing to a corner. It doesn't really work in reality. So I think you would have actually found out that perhaps it's better to tweak a bit that orientation, including as a parameter of optimization, perhaps maximizing integration or choice or whatever it is, including the context. And you will find out that you don't want to be pointing the entrance into the corner. So that's I mean, obviously it's a technical stuff that you have enough on your plate to actually deal with that, but as a further reflection. Then another little comment is you seem to have this beautiful structure wrapping around the bridge and then coming down to the ground with the same rhythm. So if it's every 1.5 meters in the canopy, it comes down as 1.5 meters or whatever the distance is to the ground. And perhaps it's a bit too much. Like at the end of the day, the structural requirements in the canopy and in the footings are different. So there's no need to actually come down with as many structural elements to the ground. And just the third one, I remember once working on a similar project where we were having to shade a bridge. It was a long distance. And one of the problems was that the material of the canopy itself would heat up and almost fry out the passengers below. So the people passing below, because it would just heat up so much. So we ended up looking at hundreds of options, ceramics, or that wouldn't heat up. And that was one of the problems. Like basically, you wouldn't get heat from the sun, but the canopy itself was uncomfortable. So there is this bit of material choice that obviously took us a long time to decide, but I would imagine that would be the next step. But the only reason I'm making these comments is because the presentation was clear enough to identify what were the points where we should be commenting. So congratulations for that.
Thank you. And then you're absolutely right. In terms of, you can see there is such a density on the structure that sometimes, like we discussed yesterday, until which point would be sustainable would you introduce so much. And I think it's definitely due a further optimization on understand the bottom structure that has certain rhythm, and the top has different requirements. So our next step was to then start refining those and treat and separate it. So thank you very much.
I might continue in that because it's also more related to the structure of the bridge. Congratulations, you really nice presentation. I think you did a really good job in actually evaluating different options and optimizing it based on the metrics you suggested. What I think, because we had a similar project like doing a structural barometric bridge a few years ago, and there an architect, Martin Knight, he's bridge designer in UK, he told us like there are 3 important aspects about a bridge, like how you actually access the bridge, like the landing points, the view from the bridge, and the view at the bridge. So actually you evaluated really nice spots, which are the most comfortable ones on the bridge in the end, but the view from the bridge, you suggested in the video in the end that there is actually the surrounding itself may suggest some nice scenery as well, but this could actually be a focus, like which places on the bridge are supposed to stay, because it shouldn't be just a transit from one to another, but if it's a really nice place and you make it comfortable, people should be invited to actually rest there and enjoy the nice view. So maybe some highlighted spots, that's on one side. And on the other, a structural input, because if you would go into further detailing with like how to densify the structure close to the legs, but actually you can have thinner diameters when you have like the range, but it's more like how you can structurally optimize your model also based on that. But I think on environmental performance, you did a really, really good job. Thank you for that.
Thank you.
Thank you.
I just have a quick comment. it was a great presentation, and I think it did very nicely in the. I really loved the ending and how it was used as a building and how that was guided through a wind simulation. That makes total sense, I think. What I think my only comment would be in the beginning where you're optimizing based on distance. So distance is a very hard constraint, and obviously what you got was a straight line, right, from A to B, and that's okay. In the real world, there are costs, you know, infrastructure that has limits and all these things. But if this is also a part, like a project that is meant to be, for example, again, as a public space, you could consider like not having such a hard constraint and perhaps putting your other constraints that you use later, like views or solar radiation, into that search. And that would just give you a more interesting shape, let's say, maybe with some pockets of public spaces, something like that. That's my only comment. Very, very good job.
One very quick comment. First of all, those that spoke before me have covered me, but one thing, you, as a suggestion, what I would do personally would be to split the whole optimization process into smaller parts. Okay, so you try to optimize one thing, then try to optimize another, and you, as a designer, you are going to put all those things together because there are going to be a lot of political and technical and non-technical, influences on your design. After all, it's not going to be one solid technical design that is informed by a machine. So as long as there are humans that do this kind of work, what I suggest is that you simplify your optimization workflow. Other than that, it's a fantastic work.
Thank you very much. I must tell that the entire work on this project in studio was a continuous reduction, not even optimization, because we have started from a network of bridges, and then halfway we realized that it's too big of a problem to be solved in such a short time, and so the real work on the environmental optimization took even less time than it should have. So that's partly the reason why it's obviously halfway.
Should I go? Yeah. Okay, thanks guys. I thought the presentation was fantastic. I had also written some of the comments that have already been said. And I think it's really important to think about this as a space that you can stay, also because the footprint, the physical footprint of the operation is quite large. But I think it also needs to be sort of cross-read or cross-referenced to some extent with the social context that you're dealing with, which to my understanding or to my knowledge is a delicate one. So I would invite you also not only to think about like the potential of integrating spaces to stay, but rather also understanding how you design these spaces. And I was thinking, you know, now you just said, Sergey, that you weren't thinking or you had thought about multiple access points, but I think this might be something that is worth sort of re-reflecting on in the integration, specifically in relationship to the social context. The other thing that I was thinking is that in relation also to the comments that we were talking about, this kind of excess of structure, that can potentially or could potentially be justified if you integrate other functions. So for example, in the pillars, you've integrated vegetation. So how could this potentially work with nature-based solutions for filtering or capturing or harvesting water? And I know that in Johannesburg, a couple of years ago, there was actually a big issue of access to water. So that might be something that's interesting to reflect on. How can you integrate other functions within this kind of structure to be able to justify in some way the mass of the structure through other integrated performances? So thank you guys.
Thank you.
Thank you, Matilda. Anyone else?
Thanks.
Manuela? It's okay. So we proceed to the next group.
Hi everyone, do you see my screen?
Yes.
Yes, we do.
So try to keep it shorter as you are group of one.
I will try. I will try. My project is about a students' housing program. I start actually to ask myself, first of all, my project is located in Saudi Arabia, which it's hot. But I asked myself, first of all, is it unbearable climate we have really in Saudi Arabia or not? That's why I'm trying to explore that information, if it's real, it's really unbearable or not. My site, it's located in the north of Riyadh, nearby the university campus. My objectives is create a shaded public bazaar area and enhance comfort on terraces for the students there, and inform the design decision by the environmental analysis, as it will shown in the next slides. First of all, we have the chart of all the hourly dry bulb temperature. Then I'm trying to see the hottest period in our climate, that it's exceeds more than 30 degree, show 38% from all the year, showing it's more than 30 degree. Now become about the wind, the same strategy to show the wind speed, showing the 80% of per the year, showing less than 5 meter per second, and the third parameter showing the humidity. So I'm trying to find the above of 20% per the year in Riyadh, which get result 43% for all the year. Now I'm trying to find again per the hottest period, which is become between May and September, and again between the 8 a.m. up to 8 p.m., showing when I'm combine some factors or some influences like temperature or winds or even the humidity, and it's shown when generate the temperature which above or exceed 30 degree, and the wind speed less than 5 meter per second, it's showing 27% again per the year. When I'm trying to add the humidity, it's shown just it's around or approximately 1% per all the year. So I move on to my area, and showing the total amount of sunlight, and seeing the casting of context around L shape around my site, and just basing my project here, and showing that in the left the key legend, showing now the percentage, show so in the bazaar and public area, showing approximately 40 percentage. It's under the sunlight. That means 60% we have it's shading, which is good. I noticed that in my ground floor plan, there is here which in the dashed ellipse, there is my coffee shop on the ground floor, but it's showing more yellow surfaces. That means it's getting a high amount or high total amount of sunlight. Then I want to focus on that, because it's a coffee shop, and I want to try to explore and find solution there, and I focus there, and I'm trying to add shades to trying to explore. I'm not really sure if it's possible or useful if I add some shades there and find that that days which is under shaded, and if we notice that in the above of terrace it's whitey, that means it's not become under the sun let's say sun rays. So the darker surfaces meshes, it's showing it's useful if we use shaded or pergola, for example. Now moving to wind and showing the wind per the year with the different months, and if we notice that it's most of them it's become from the north side. Now I'm trying to find in the public area and the bazaar, if it will be annoying, the wind, it will be annoying or not for the activity on the public area. So I saw that in the left of hexagram, it's showing the highest bar chart. It's showing with the domain between 0 up to 0.5. That means the wind there, it will be a little bit let's say lazy. Now I'm trying to show that the wind races through the terraces and the capsules in my building, and here showing the same, which the most it's become with that domain showing between 0 up to 0.5, but nothing more than 7 meter per second. This my wind pressure facing on my north facade, and I'm trying to now design the envelope, or let's say the skin of my building, which is also based on environmental analysis. This my building become with capsules, aggregating capsules. Now this my activities there or zone categories in my building. Now I depend on my activities, I change the pattern of capsules or the sizes of capsules, and generate the openings for all of them. Now it's become the same let's say offset. Now I just see again that the sunlight becomes with my faces, and we notice that the purple one which is in the north side, and the blue one which is already shaded by the cantilevered floors, it's become blue. On another hand, in the west side, it's become red, or let's say some of them it's become maroon. Depending on that, it's become an inverse relationship between the faces and the let's say the sun rays on our capsules or our facades, which is become a high sun rays on my facade. It will become a small opening area. Now I'm talking about the vegetation. Actually, from my humble point, I see it will be useless if I cover my rooftop by grass, or because nobody will be there, and by the way, it will be water consumption. So what I did, I take lower faces, and which get the highest let's say total amount of sunlight, and take 50% of them to make let's say vegetation or let's say trees there. This is my bazaar. some renders, terraces. And if we see that the right picture there, it's showing when it's casting shadow between from the neighbors. When the even it's in the north, sorry, south side, but it's become bigger than the above or upper floors. Why? Because it's casting shadow. That's it. Thank you.
Thank you. Right at the moment I was giving you a warning. So feedback? Let's go first.
Perhaps I can start.
Thanks.
Okay, thank you very much. It was a really insightful project. I've particularly appreciated your architectural language and how you have curated the voids, this airspace that are geometrically quite interesting. And linking to that, I wonder if you have thought at a certain time of your process to focus more on these outdoor spaces than into the building. I'm wondering if it could have been also interesting to consider the building as let's say, a background of this space. And I have a question if you think that also overpopulating the facade with many design variation, do you think it can create a certain, let's say, pollution as you have many targets to be fulfilled? I wonder if from, keeping the conversation on a language stand could have been also a viable strategy to focus on the outer spaces. Yep.
Yeah. Can I?
Yes.
Yeah. You're right. Actually, I'm focusing on the external, let's say, external comfort, because as you said, we have the attractive path which reduct the capsules. So my experiment here to see if it's comfortable to the students sit outside with our dry climate. But what I get now, I think it's bearable to sit outside now with the ventilated, continually flow wind.
If I can continue on Manuel's point, I agree that the language was really beautiful, and I think it's even beautiful from a technical standpoint. So if you really want to explore, I think different shapes and whole design spaces, I think this sort of language, the language of capsules and almost like a cellular automata, is a very good start. So if you were to expand the exploration in the future, this is a very good start. It's very open-ended. You can explore many different shapes that might not make sense, but might lead to something interesting. And the other thing I liked and I appreciate, I think in the last render, it was obvious. I like the human scale of what you did. Like we could see the background of what is the modern sort of construction right now, right? Everything is big and fancy and very ventilated, mechanically ventilated and everything. But what you did is actually what we see in the urban areas, or at least what we rarely see in those areas if we get to see them, where it's much more human scale, much more understandable, like approachable. I really like that. And yeah, it was very simple. I think simple and powerful approach to create the shapes, and it was very good. That's what I want to add.
My only comment is that in your presentation, the solution of this building block appears, I think I mentioned it in some of the presentations, appears too quickly. And I don't actually see what was the process that you followed to make the decisions. I can see later on there are areas of self-shading, there is a canyon. I mean, that you've thought about it. So I'm not saying you haven't, but it doesn't express itself in the presentation because it just appears in one. So one thing I think you could have actually tried is, like, I'm sure you did run a or a Galapagos or some form of Wallace sort of like optimization. I would actually have created a video of this process taking place and you trying to extract intelligence out of contemplating it and try to see if typological intelligence emerges out of it, because I'm sure it will, and it's a form of actual research trying to see what is the computer trying to tell us when it's sort of like figuring out holes in the back or in the bottom or whatever, and how those typologies relates to what we already have in the back of our minds. So even that form of basically making a nice video of the process itself will help yourself explain it, think about it, and others to grasp it.
Thank you.
I can only agree with
Teresa, yes.
before, like also for, thank you for a really nice presentation first. And then I think for the storyline, yes, the building just appeared, and the reasoning why you actually chose those shapes came later on an explanation. So it would have been good, like if you started with the explanation first and then show the building, which was really nice that you focused on the outdoor space, not just in general, but actually related to the use of the building. Like you were saying, this is where the coffee is, so people will sit outside there. So actually it's a really good linkage, which outdoor spaces, which will be used in which relation to the building. So that's a really nice thing you did. And also for the wind comfort study, looks like really concise and really good approach. Thanks.
Thank you.
Perfect. Let's go to the next one.
Yeah, just a second.
Group number 9. Yes. Shoot.
Good. We are group number 9, Navapan, Jonathan, and me, Benno. We're presenting a Bangkok residential today, means program is residential. Like first we start with the context. Here you see like the context or the like it's in Bangkok. The site is located near the city center in Bangkok. On the next slide, there you see that like the plot. It's a yeah, we found a plot. It's a large plot for a residential program. It's 135 by 73 meter. You see it here. It's a very heterogeneous neighborhood, like bigger buildings, small buildings, like, and on the next slide, you see an image which face west. It means it's very flat, the whole building. The buildings, so the neighborhood, they give not really shadings, and it's also residential area. Yeah, next we start with the climate.
And according to the climatic issues, first we need to comprehend the climate as an ecology in order to know how can we use the data as a resource. So we start looking at the overall temperature of Bangkok recorded from the Suvarnabhumi International Airport, showing the hourly data of temperature within the whole year at the average range between the 30 degree to the 36 degree. Then related to the season, the interesting thing is that during the winter time, there are more radiation than the summer. This is because like related to the cloud density, which we can see on the humidity bar below. We guess that during the rainy season, it could help diffuse the direct sunlight and solar radiation from the sky. According to the relative humidity, around 3/4 of the year from January to October, wind direction mostly flow from the south side, which brought the humidity from the sea. This is known as the summer monsoon. Meanwhile, the last period of the year, the wind will move from the north or the mountain part, which bring the cooler air called winter monsoon. Therefore, another issue is a flooding problem. The common period of the flooding are in between September and October, where it's the end of the summer monsoon and rainy season. And also direction of the sun part also make a major impact on the increasing of the air temperature and heat island effect. The more perpendicular the angle is, the more temperature it increase, which unlike European city, Bangkok is a tropical country that people normally avoid facing directly to the sunlight, and it could easily burn the human skin within an hour. So by living under the shading area would be a suggestion, and this issue will be developed in our further design principle. And for architecture and engineering, we investigate how the climate related to the social activity and found that 30% of the housing energy consumption comes from the air conditioned operation. As one of the most density, Bangkok has not many parks or forests to reduce the heat island effect. There's to say like 90% of the building needs air conditioning for cool down the interior air temperature. So we would like to propose the strategy to help reduce temperature and protect the building according to the data we have. And with the idea of passive cooling strategy, which is the project, like for example, Thai vernacular architecture will be our model roles for our case study. We have thought that perhaps we could turn our problem into opportunity to design a strategy with mainly focusing on the passive cooling. And we expect that the goal will achieve the result, including the temperature reduction, less solar radiation, and maximize the ventilation with the passive system. And Jonathan will continue on this. So we try to extract the main principles from the vernacular architecture. And the next one, we see kind of the most important principles. If we start from the ground level, there's this principle to elevate the building in order to increase the ventilation. We have external shading systems. We have a jetted roof. We have a slope roof in order to increase the cross ventilation. We also have a timber structure and bamboo for cladding. So we had the question how to integrate these principles into our design. So for our form optimization, we try to include all of them, but we started with the regulation. For the regulation, we set a parameter of 6 meters to set back. Then we set a parameter for the height limit of 24 meters. Then we use this concept of box-in-box concept to insert a volume inside in order to have an external skin to increase the ventilation and we also set back the ground facade to avoid the direct sun and to create a self-shading. And we opened the ground floor from the vernacular architecture strategy in order to have this cross ventilation. And we integrated with 3 different vertical atriums in order to make the airflow through the building, through the common areas and the corridors. We created a roof slope strategy and we oriented this roof towards the wind direction from the south. The result is integrated wind strategy in the building. We ran our optimization process with Wallasey and we selected the average options and the top best. We have here a comparison between our best 6 options and we took the number 5 since it has the lowest temperature, inner temperature, and the lowest roof solar radiation. And what we managed to do was to decrease the temperature of the building. The typical mean building surface temperature in Bangkok is around 35 degrees Celsius, and we reduced it around to 31.97 degrees. And after we get the results, we start wondering how can we design and define the location of the opening on the facade, and what will be an input for our data. So in this stage, we start thinking about how can we locate and create the opening on the facade. So we look at the wind pressure on the facade surface to see where is the most possibility of the wind to flow or enter through the building. And we have mapped out the 8 direction possibility of the wind that create the pressure on the facade surfaces. To use this data, we have overlaid the wind pressure of 8 different directions and implement on the pattern of openings according to the pressure value happening on the facade, where the max pressure or rate are the most opening area and the minimum pressure of blue will be the less opening. And also solar radiation will take part as a self-shading strategy. That is to say the solar radiation will be for subdivided the diagrid to increase the self-shading system and the wind pressure to minimize and maximize facade opening, which we have set the opening percentage according to the daylight factor. We have analyzed the overall facade for daylight factor to understand how can we set the minimum opening requirement for our facade to provide a sufficient light. We found that with the 40% openings, the interior space will have the daylight factor between 4 and 5, which during the day in the indoor space doesn't need to use the artificial light. In parallel, the section diagram shows the cross ventilation from the southeast to the northwest, where the indoor hot air can flow up to the roof through the porosity of the atrium structure before moving out of the building. This is the measuring the result of our strategy and the facade radiation. And lastly, we are questioning about what is happening behind the facade. So in order to consider about cross ventilation and how the wind have an impact inside the indoor space, we look at the wind speed on the empty floor and analyze the area where it could achieve the comfortness according to the Lawson criteria. And we found that the indoor space have different values and different directions when the wind flow through the facade. And and we end up with a strategy about using the wind velocity behavior to define the program within the space. We believe this data will help improve our design in terms of programs and circulation in further process. So as a conclusion, we have achieved 3 optimal results, including reduce building temperature, create cross ventilation, and apart from simulation, we are successful to use structural elements with carbon neutral based material. So this will be the end of our presentation. Thank you.
Thank you very much. Now, let's go for the comments. You can stop sharing your screen.
Yeah, just a second. Okay. Yeah.
So, tropics again. Who's going to go first? Come on, don't be shy.
I'll do.
Teresa, yes.
Thank you for the presentation. I think it was really nice that you actually showed also the research which you've done for the vernacular architecture that is built there. I think it's a really nice background how you start your storylining, and also like the way that you actually come up with a whole sustainable concept for the building itself, also going in detail with the materials and the cross circulation and ventilation of the buildings. I think it's also a good thing that you visualized it in a really nice way in the end. Also the architectural rendering, I really enjoyed that as well, because I think it's really from the beginning till the end, a really complete study which you did, and I think you presented in a really nice way.
Thank you. Thank you.
I can maybe go now. Thanks so much, guys. I completely agree with what Teresa was saying. I think it might be interesting now to continue and look at how the building optimization then feeds back into the design of the inner box, let's say. And I think you guys hinted at that in some way, but it might be interesting also to look at, how people inhabit space in Bangkok, and what types or different typologies of space that you can generate within the building, from private to semi-public to public spaces, and maybe look at how you could integrate, different sort of modes of inhabitation within this kind of optimized sort of built environment, maybe also related to the hours of use of the different types of spaces that you then go and generate. I was thinking also it might be interesting to sort of have a post-reflection on what is the impact of this building in relation to the surrounding context. So does this building allow the context beyond the building in itself to perform differently? And what are the benefits maybe that it could provide in that sense? But congrats, guys. Thanks.
Congratulations also. Good work. Just a quick comment. In your case, the optimization was not fabricating the building typology, as we've seen in the previous ones, where the type of building in a way was conceived by the cerebral automata or whichever. In your case, you just brought it and you simply made some tweaks into it. But somehow in your description, I found it hard at the beginning to understand what were the options and what were they different, what was changing from one into the other. And I think that could have been made a bit more clear. And at the same time, the location of the circles that were punching the holes through the slabs, you could have actually introduced that as well as the building layouts, so that in a way, the optimization in itself helps you navigate many options of the same type. So perhaps bigger, smaller, more private, more, whatever it is that you are trying to reflect on how that building typology changes and how are you adapting it. Because somehow some of the decisions to me happen like, hang on, that's perhaps a bit too quickly. And you could have actually gone through that process a bit more more slowly once you've already set and decided what it was going to be based on, which I think is a good idea and a good point. But other than that, really good work and good result. I think.
Thank you. Thanks.
Any more comments? Theodore, Emanuele? No? All right, then we continue. Group number, 1 second. Go to the right Slack channel to find the order.
Number 6.
Group number 6.
Paulina, Amal, are you ready?
Group number 6. Yeah.
Sorry, I can't unmute myself when I share this. Okay.
All yours.
So we are group number 6, myself and Amal. Our project is located in Melbourne, Australia, where the climate is considered temperate. We have mid-temperature, fully humid, and dry. Our project is located in a residential area, suburban residential area in Melbourne. It is close to a park and a river, and our closest neighbors are a campus of a college and primary school, and a lot of residential housing development. So our program is basically fitting in the context. We are doing a residential apartments, and we also have a commercial part. So it's a mixed-use building. Our commercial part will be a cafe, and because we wanted it to be automated with like a lot of robots, we've allowed for quite big back of house or service area. So the main concept of the building is to be a link for the neighborhood with the park. So we wanted to create some sort of inviting volume that people can go through so that they can reach the park. In terms of aims, we wanted to explore prefab and create a modular system that basically is driven by one part, COT part that can work both horizontally and vertically, and modules that can work both horizontally and vertically. And we've used structural optimization to define those parts. And we also wanted to optimize for solar gains. And basically, this is our process. We defined, based on the context, the entry points, the common areas, the best views, height constraints, and so on. So we defined one volume, and then we optimized within this volume for better environmental performance. And we also optimized for structural. When it comes to the seasons in Victoria, Melbourne, the Aboriginals used to have 6 seasons. We've adopted the idea of 4 seasons from the European settlers. So our main research question in terms of environmental optimization is how can we reduce the need of cooling? Because there is not a huge difference in temperature, and you can see on the graph the days of in which we need cooling are a lot less in comparison to the days we need heating. So we thought with our optimization we can actually make this cooling non-existent, basically make no need for cooling. The temperature is between 10 and 35 degrees, always above 0. The sun is coming from the north, northeast and west, because we're in the southern hemisphere. We also explored what is the radiation coming from the sky. And we compared the 2 sorts of radiations, direct and diffuse. And these sort of studies informed our massing. And here Amal goes with the wind.
Yeah, so basically we did a very quick test on the hottest months that we have in our year. Actually, we do have from 12 p.m. to 6 p.m. we have some hours that we can use wind as ventilation.
It's changing the slide. I'll be changing the slides, just tell me.
Amal, can you hear us?
Yes.
Continue.
So basically, this is we generated the wind draws to look at where the winds are coming to our site. Next. So basically, for form optimization, we started with buildable area based on regulation, 40% of total land area. Next. Then we constrained our volume based on site parameters. So basically, the height limit is 15 adjacent, according to adjacent building average. Next. Next. So we used voxelization and we used linear attractor to populate our volume. Next. So our voxel size is 3 by 6. This is the module that we are testing. Next. So basically, an iteration for iteration 1, we had direct sunlight to our building and no self-shading. So we decided to change the linear attractors rules and rotate our building. As in iteration 2, we have less direct sunlight and more self-shading. Next. So based on our access points, we wanted to define our ground floor plan, and we uplifted for cross ventilation and wind flow. Next. Next. And that also affected our interior circulation and vertical atrium for vertical ventilation. Next. Next. So this is our optimized volume. Next. And this is our program where we have the commercial, residential, and services at the back where we don't need that much sun. Next, for our program. So for solar radiation analysis, we have done an annual in heating and cooling. We noticed that we have minimized the roof surfaces and we minimized the direct solar radiation. But next. But there is also a potential for generating energy from our roof by integrating solar panel systems on the roof. Next. So basically, as a modular system, we decided to focus on a cluster that is on the north facade where the solar radiation is the most. Next. And from that, we generated our daylight strategy. We have the variables, which are opening specifications and locations, and the orientation and stacking of our modules. Next. So basically, at the beginning, we ran a floor plan analysis. At the beginning, first scenario, we see a fully glazed analysis. And scenario 2, we have a solid wall. And scenario 3, we try to test opening sizes and shading system with double glazed panels. Next. So then we started looking at, since we have a modular system, we wanted to test taxonomies and different modules. Next. But actually, we wanted to look for spatial daylight autonomy and annual sunlight exposure. We have a modular system, so we tested 2 modules that are stacked, and openings are created from both sides. One side has one side is covered with shading system louvers, and we took in consideration the glare. And from that, from that analysis, we realized that we have a deep modules, 3 by 6 meters depth, and we need to have openings from only one side. So basically, yeah, next. We wanted to maximize the daylight by large openings, but also minimizing the glare. Next. Also, we were considering of how these modules are stacked and placed together. Next. So our shading system louvers proved to be useful in our strategy. Next.
Yeah, so going back on to the volume, we did some initial optimization of the actual volume and learned the hard way that using not the final modules was not the right way to go. So in the second round of optimizations, we basically had the volume defined, and we run the optimization against 2 criteria, which is maximum volume area and minimum solar radiation in the cooling period or the hot period from 11 to 3 p.m. So that we can achieve that kind of reduction of the need of cooling. So we actually found that sometimes, of course, this optimization is not applicable because when it reduces the area, of course, it is not comparable, which we are working on to fix by actually optimizing with the number of modules. But anyways, that gave us a good range of options to compare from, and we could see the architectural options that we liked, how they're working, and how those compare to a larger range of options. So we chose one option that is the one below here. In terms of radiation, we got 28% reduction of the solar radiation because of the optimization in comparison to the initial volume that we had designed. In terms of next optimizations, we are planning to optimize with the number of the volumes, also optimize certain parts of the building because the northern part has some goes the southern different, and yeah, also consider the number of volumes per floor because we want to grow as we grow in floor. So that's it.
Thank you very much. Let's go quickly to feedback so we can be a little bit in time.
Yeah, perhaps I can start.
Yes. Can you just stop sharing your screen, Paulina?
Yep.
Yeah.
Thank you.
First of all, it's really interesting that you focus on cooling loads because this will certainly be increasing with climate change, and I guess all of our built environment will have to place much more emphasis into that. As well, it is interesting that you tackle a bit an industry, the one of modular buildings, that has always proposed a very introvert type of architecture. On the other hand, I wonder, and perhaps you can share your thoughts, do you think that performance can be the only generator of forms, or you feel that perhaps a certain architectural field thinking can also be a factor in the form making? That's a question for you.
Sorry, I didn't quite understand if we can use the evolutionary solver.
Yeah, I'm sorry. It seems that the form is made by a set of environmental factor or accessibility or urban syntax. I wonder if perhaps this is my consideration. It seems that the form making process is missing a layer of architecture. I mean, it may stand structurally and it can be interesting environmental organism and may fit some rules of access. But do you think also
Yes,
some,
yes, I got your point. Yeah,
yeah.
so well, unfortunately, this is still work in progress, so we didn't have enough time to finish. Definitely, we have architectural features that are basically based on those parts that aggregate and give a certain feel, but we just haven't got to that point to develop the project. So we were focused at the moment at structural and environmental. So what you see is basically the structure of the building. But yes, there is this part which we have only explored in small clusters and is not part of this presentation.
Okay, so you're saying this is a meta architecture. It's an a part of the process. I see. Okay.
Well, yeah, we just have 10 weeks or whatever. It's that's where we managed to get to.
I have again one very small observation that you also focus a lot on optimizing the form for solar radiation, and particularly on the cooling period. Okay, and while starting from there, while this is a good start, okay, you should focus a bit more on how this geometry actually performs in real life through thermal simulations, through energy simulations, because the way you're designing this modular building, basically you are allowing a lot more envelope to be exposed to the outside air without this envelope actually contributing in any positive way to the energy balance of the building. And while the optimization study, the computer tells you that this is the optimum solution, this optimum solution is affected by this logical fallacy. So you, while not being particularly wrong in the early stages of design, you should really, and this is for all groups, okay, don't be blind against optimization studies. Be very careful on what you're optimizing so you don't end up with a garbage in, garbage out situation. I'm not telling you that this is what you did. You start correctly, but the next logical step in your analysis and evaluation of this form should be energy simulations and how this envelope you design actually influences the energy balance of the building. And this is not for you, again, this is not for this particular group, this is for everyone.
Yeah, I think it's just a matter of time, but that was exactly, we were working on the slide before, but if we were the last group, you would have seen it, but unfortunately.
No, you did a lot of work, okay? And this is a very complete presentation of what you did. And I'm actually amazed by your progress and how you moved into, integrating those tools into your workflow, which is what we want you to show us today. And so from this point of view, you did perfectly fine. But as you say, the next step, the next logical step to this thing would be, to do more detailed energy simulations.
Thank you.
Cool. More comments from the jury?
Just a small comment. Be careful because this is an error I've made in the past. I focus on cooling optimization, but then in winter there were big problems. So just make a verification of how your building works in winter at the end. Because having a purely summer optimization can be really risky, given the chart of the two seasons.
Okay, good point, thanks.
Any last comments from Eduardo? I don't know.
Just quickly, looking at your plan and the emergence of the courtyard, I think your optimizations all have a field condition that would lend themselves quite easily to be expanded to create the landscape fabric around it. So almost you would have two for the price of one almost if you made a bit of an effort to turn and design part of the access and part of the landscape around it as part of the same process. But I mean, on that, quite good project, really.
Excellent. Thank you to all. Now let's move to the next group. It's group 4, I think. You ready? Perfect. Just a little more patience. We have 3 more groups and then we're done. Group 4.
Hello, everyone. My name is Natalie. Together with Sachin and Harsh, we are group number 4. Our project is located in Moscow. I will make an introduction to our site location and project, which we've done with the stress on the environmental analysis component. Then we will explain in more details each part of the simulation. The statement. The city today is lacking the community space. The modern architecture has created a number of single function venues which are often separated far from each other. Even the so-called multifunctional mixed-use buildings are really mostly the retail centers with an entertainment component, and they are usually located far from the residential areas. The only areas fully adaptable to all kinds of public activities are parks, but there the climate issues came into play. Moscow is located in sharply continental climate zone with the annual temperature differences over 50 degrees, cold weather, hot summer, and frequent rains in the mid-season. All together, this call for the sheltered public space, context and climate. Most precipitation in Moscow falls as rain, but in winter month, almost all precipitation falls as snow, forming firm snow cover. Typical high temperature in warm months are around 23 degrees, but during highest waves, daytime temperature highs often top 35 degrees for sometimes 1 or 2 weeks. In the winter, temperature normally drop to approximately -20, though that can be periods of warms with temperature rising above 0 and colds when it reaches -35. Duration of daylight varies from 7 hours on December to 17.5 hours on June. The site of the community space is located in the historical center of Moscow on the junction of the New Ubud Street and the Boulevard Ring. The urban void on the corner is the footprint of the historical building demolished in 1994. The wide and straight New Ubud Street cut through the historical development has created an obstacle to the pedestrian circulation and at the same time opened the space to the winds. These diagrams show the correlation between climate limits and our design workflow. Project. We run simulations to explore the limits and possibilities of our site plot. Environmental fitness objectives for the form finding include maximizing flat roof to create public lifted garden with a nice viewpoints and collect rainwater to the vegetations. Minimizing north facade to reduce the heat loss in the building. Reducing building shadows on the surrounding buildings. Maximize the ground canopy to create a shaded space for pedestrians. We use the result of the simulation as a boundary box where the constraints we took into account define the basic shape of our design. After we focused on the 3 main components for our building, the light wells, the skin, and the semi-door plaza. Our proposal addressed the challenges of the design a building in the contrast Moscow climate, where one needs to protect from the direct sun and glare. And for that purpose, we have introduced the dynamic fabric screens, which can react to the sun and wind. Also, by creating vegetation on the upper level, we aim to reduce the heat gain in the summers and contribute in solving issues like urban heat island affecting the city of Moscow. And now we will explain the process in details. Sachin will start with explanation of our research questions.
Hi, everyone. So the important aspects of our proposal were based on 2 important questions. How can climatic design study influence the form finding strategy of a building? How to design for cold climate of Moscow by considering harsh sun, as well as high wind in the Moscow region. Site analysis. We observed through our studies that due to the low angle of sun in winter, there's a major solar gain. While in summer, there's a high angle of sun that provides high radiation, which needs to be blocked. We observed through our analysis that the daily temperature is maximum between June to August and minimum between December to February. The climatic study charts helped us to understand diverse range in temperature and this diurnal variation between the heating and the cooling periods. The daylight analysis showed us that the proposal needs to look into optimizing both the solar and daylight gain. The wind analysis showed us that the site is open to winds from all directions, which is a serious issue in winter as well as in summers. We studied psychometric charts for a site, and we observed that the passive solar heating and capturing heat gain can aid to improve the comfort at our site by about 40%. Other strategies like evaporative cooling helps us in a small extent in the cooling period. These help in design to improve comfort percentage from 4 to 45%. Now methods.
We then started looking into what methods can be used to optimize the design. So we looked into 4 major methods: evolutionary form finding that defined our geometry, then environment analysis, further daylight analysis, and CFD analysis that addresses various aspects of a design. Various simulations were performed incorporating the environmental parameters to help derive the final form. First, we have a list of research studies that helped us define the design objectives for the building which we want to optimize. The first one, a research on solar envelope, was done to derive the initial volume and the required insulation value for comfort solar gain, which helped set as a baseline. Then, to develop the building footprint from the site in order to create a public space, the insulation area on site and the immediate site fabric was looked into. Further, the base building floor plate area was defined as per the facade to avoid heat loss, and the orientation was determined by maximum radiation angles of the sun. The facade was developed by attaining a maximum solar gain from low-angle sun in the heating period, and a negative slope was created as self-shading on the east, southern, and western facades. Thus, the floor plate areas were also defined as per the horizontal shading factor of the latitude. Further, for the cooling period, the maximum high-angle sun helps to define the roof area, which is also used to collect the rainwater. Another aspect is understanding the casting of shadows on the site and the context and the form, which should minimize as per the bylaws. So based on the environmental studies, these were the fitness objectives: reducing the heat loss in the building by minimizing the northern facade, reducing building shadows on the surrounding buildings as per the bylaws of Moscow. In order to create a shaded space for pedestrians, we introduce a fitness objective of maximizing the ground canopy, maximize a flat roof for creating the negative slope for building and self-shading, and maximizing the other facades for solar gains. Here, it's important to note that at first, the best options of each fitness objective were studied to define baseline values that helped us to gauge the final selections, as well as prioritize the fitness objectives in relation to each other and the context. These are the final prioritized fitness objectives and the 4 best variants which were chosen by comparison. After several attempts and closely testing variations with climatic analysis, we observed variant 1 works the best. The final optimized massing was reassessed with the environmental studies, and it was noted how in the cooling period, the self-shading helps block high-angle sun, and in the heating period, the huge roof and the east, southern, and west facades help in solar gain. Now we would look into the results in conclusion.
The 3 optimized components of our building that were result of our studies were the light wheels, skin, and semi-indoor plaza. The introduction of light wheels in the building instead of the introduction of light wheels, 2 light wheels in the building instead of 1 came from our initial studies. This intervention not only improved the daylight in the building, but become the structure that supports the floors and follow the same principle of the facade and brings the structural elements inside. We studied that the wind patterns around our site and also in the vertical sections, and observed the average speed of 1 meter per second around the building that is suitable for sitting long time as per the standards. And also at certain times of the year, the speed varies both in the summer and cold period. Hence, concluding from our climatic analysis, we decided to wrap the building in a skin of structural timber. An important aspect of our proposal includes creating a public plaza on the ground and the lower level. It extends its canopy for protection from rain and snow. After mapping the pedestrian movement around our site, we ran a few simulations and created a seamless pedestrian movement, crossing in diagonal motion and cutting the urban plaza on the lower level into smaller parts. We ran a few simulations for winter and summer winds, and that we got from our previous environmental analysis. We observed these invariable winds form a pattern around our building. Hence, we can see the variations of wind more closely to our context, which wasn't possible with windrows diagrams. The timber frames are flexible and use textile screens as a material, which is one of the recent innovations that could not only protect from the wind and sun, but also help in cleaning the smog particles in the air, since they have a filter for nitrogen oxides. This is the view from inside the semi-indoor space on the ground level and benefit from the self-shading of the building. It provides shade to not only the pedestrians, but also creates a covered public forum for urban activities that is missing in Moscow today. Movable textile screens can be controlled to open and close as per different wind conditions. So our proposal integrates climatic methods and strategies in form finding, natural lighting, self-shading, and reducing the overall heat gain of the building. And this is a small video for that. Yeah, thank you.
Thank you. Let's jump to comments very fast. Congratulations, guys. So, who's going to be first? We're getting slower as the day progresses.
I can start if you know what it
Please.
was. Thank you for the really nice presentation. I had experience as well with like a similar climate once in Kazakhstan, where if you have the hot summer and the harsh winters. So I'm really impressed how you handled the situation. And I think it's really clear how you stated the optimization process in the very beginning, like which criteria did you actually approach, and how you presented them was really nice with the spider chart that you showed, okay, which factor influenced the design to a certain extent. So in that sense, I think it's really the storyline, how you came from one step to another and how you actually finished with this really complete CFD study in the end. I think it's a really good way and complete project you made. Congrats with that.
Thank you.
Next, Matilde.
Yeah. I think you guys have done a really complete and very clear presentation, so congratulations to that. I just had one question. I understood that the skin is a dynamic skin, and I was wondering how that would behave. Like, you focused a lot on how that would behave in summer, but how that would maybe behave in winter in relation to the snow that we were talking about, the firm snow cover, and maybe, you know, how the kind of heat accumulation in the building could allow to sort of prevent that. Maybe that's something that I would have liked you to go into a little bit as well.
What we thought was, because the form of our structure has a negative slope, so I think in terms of snow, it automatically helps us to create that like a flow of moving the snow from the top to the bottom. But as you can see from our parameters initially, we wanted to also collect a lot of snow and water on our rooftop and take it down to the ground, and which can help us in rainwater harvesting.
Yeah. Usually when we have strong winds, that's not a problem of the snow which is falls and stays, it's just falling away. When it's the snow is falls and stay, we don't have strong winds. That means that in the canopy on the pedestrian part, we can open this shading system only when we have strong wind in winter, and close them totally, like leave them open totally when we have like normally coming down snow. It will not stay there.
Okay, any last comments? Any other comments from the jury? No? Cool, then we can continue to the next group. Thank you, guys.
Thank you.
Can you see the screen?
It's coming up, group 1, right?
Yep. So, yeah. So can you see the screen?
Yes, now we can see the screen.
Yeah, cool. So good evening, everyone. Our project is titled The Modular Edifice, and we are group one with Krishna, Alex, and myself, Keshav. So why modular is because modular objects have entities which repeat like cells, and modular thinking can also be linked to sustainability as framework used to build one module, can be used to repeat, and hence it can save money, material, as well as time. So our project is divided into 6 parts. So the first part is the site analysis. So the site is located in Mumbai. It is located on the eastern coast of Mumbai in between 2 main roads and the rail track. The site is very accessible by road and rail, and the nearest railway station is about 5 minutes walk from the site. The site lies in between the commercial and industrial parts of the city. Then we went on to understand the environmental aspects of our site. Most of the radiation in our site is incident from the south, and the predominant wind sources from the west. Wind is very critical to a site as the site is very humid, and as it lies on the coast, and cross ventilation is it's necessary. The temperature is actually very high throughout the year, almost above 30 degrees throughout the year, 30 degrees Celsius. And the high radiation period is from October to April. We looked into humidity since the site is being very close to the coast. The site is very humid throughout the year, and we observed an inverse relationship between the humidity and the wind speed, as you can see in this chart. Then Krishna can explain the next part.
Yeah, so we wanted to address the lack of public spaces in Mumbai. So one of our intention was to integrate a pedestrian movement into the site and create a public pathway generating activity and providing retail functions supporting it. So from this annual thermal comfort percentage graphs, we observed that the percentage of comfortable time is fairly uniform throughout the year when there is both sun and wind. But when the sun is shaded, apart from the months of March to May, there is the comfortable time percentage is significantly higher, and as expected with sun exposed and no wind, the percentage of comfortable time is the lowest, and with the highest percentage of heat stress. So based on these understandings, we did a basic thermal comfort analysis. Keshu, can you go to the next slide?
Can you see?
No. Yeah, sorry about that. So based on this understanding, we did a basic thermal comfort analysis of the site for the first period, where there is a significant decrease in the thermal comfort levels, and for the winter periods of which the thermal comfort levels are significantly similar to the rest of the year. So due to the large size of the plot and the absence of significant shading buildings in the context, the thermal comfort levels are relatively uniform throughout the site, except for these areas with denser vegetation. And so we decided to retain these regions and develop this into landscape green areas to which the pedestrians are attracted into. And then we combine these, next slide, and then we combine these with the existing potential and pedestrian activity of the roads surrounding the site to develop this network of paths, which further makes these smooth walkways through the site. And from these paths, the left out larger areas form the initial footprint of the building, which is then further optimized. So Alex can take it further.
Yeah, so then we went on and referred to the optimization. Can you get the earlier slide, please?
Yeah, sorry.
Okay. Yeah, so then we went on and set up the optimization, like we're waiting. Okay. Yeah, the earlier slide, please. The first optimization slide, please.
Yeah.
Yeah. So then we wanted to optimize the overall geometry of our building based on environmental aspects, as well as to promote the eastern view towards the ocean, and also to increase the southern facade to promote the shadow on the northern part of our site, as mentioned earlier, to promote the thermal comfort for our public spaces. And here is how the optimization, the initial optimization ran. So we can go for the next slide, please. Then we analyzed the results. We did several simulations. This is the final one, where we compared the volume of the building and the overall radiation intake throughout the year of the building. Then please go to the last slide where we showcase the chosen iteration. The next one. So this was the chosen iteration that fits all our criteria, and also we enjoyed this design. And then we went on to develop our form further based on this form. Yeah. So
then we went on to understand the programmatic potential of a site. So then we took the program of a co-working space because as I showed earlier, the site was in between the commercial industrial parts of the city. So then we went on to formulate the different programmatic requirements, which are open desk, shared pods, private meeting rooms, conference rooms, and a library. We divided them. We developed modules based on the octahedron because octahedrons interlock into each other better, and they give us the structural rigidity. So then, based on these octahedrons, we developed 3 types of modules: so small, medium, and large, based on the programmatic requirements. So this is just like a view of a smaller composition. So then, so we had the form which was given to us by the environmental optimization. Then we had the material, which is these timber modules, which are these octahedrons, and then the function, which is the co-working space. So then we wanted to find how to unite these 3 parts. So then we resorted to aggregating these octahedron modules to form the function of our building. So this is the final aggregation shell that we further took on to do further environmental analysis on our building. Then Krishna can.
Yeah, based on the structure analysis, we then took the form and positioned an atrium into the building, and the size of the atrium is actually determined by its relation to the height, allowing the daylight into the interiors. So then we went forward and did the daylight analysis, and we started with considering the exterior walls as a fully glazed panels, even though we showed that this outcome was not going to be positive, and as expected, it was not. And although the 100% of the floor area received more light than required, than the required luminance value, but about 78% of this received about 100 lux for more than 250 occupied hours, which is way higher than desirable and not really inhabitable. So then we looked at various patterns of opaque and glazed panels to see which options would allow us a more desired level of illuminance. As you see, the first pattern reduced the amount of floor space receiving 300 lux luminance to about 80%, but has a reduce in annual sunlight exposure to about 40%, which is lower than before, but still much higher than what is desired. Then we went ahead with the second pattern with the glazing reduced just to 2 panels. And here we observed that the space received desired daylighting illuminance reduced further to 76%, but the glare is now reduced to 32.5%. And another step we took was to increase the glazing in the atrium walls, which further increased the daylight availability to 90%, and relatively lesser increase in the sun exposure. Even with this, we were not at the solution that we were looking for, but the values indicated that the direction we took leads to finding a balance between the desired daylight and reduced glare. So we concluded that we need a further level of diffusing of the facade panels to reduce the glare, but maintain available daylight. And we looked into radiation analysis to inform this further subdivision of the panels, which Alex will explain.
Yep. So then we went on and analyzed our whole building, whole facade, based on a yearly radiation to inform where we actually need to put an external envelope to decrease the sun exposure for the interior of our building. And also the second aspect for this was to promote the wind, but I will talk about it later. So then we chose around 60% of the most radiated panels as a place to place our facade panels. So the next slide. Then we developed a system for the active shading and active wind inflow panels. That is the next slide, please, because we don't have time. Yep. So then we place the panels. Next slide. Yeah, then we developed the active system that's based on the sensors, which changes throughout the day, and also that is a support for the natural ventilation that can be used during the night hours when the wind is actually colder and promote the natural ventilation. yeah, then go for the next slide quickly. Just this quick analysis on how opening and closing of the facade increases and decreases the radiation intake of our building, and then go.
Yeah, so then we decided to do a post-design analysis on a building with CFD because Mumbai is a very windy city with an average speed of about 10 miles per hour, and we used Lawson's criteria for wind safety. On running the simulation, we realized that about 50% of the site is safe for sitting in short and long times according to Lawson's criteria. So the area exposed to harsh winds can be reduced by using vegetation, which is shown in orange. So yeah, so this is just another view, and so this is how the CFD analysis looks like. So then we ran the thermal comfort analysis with the vegetation to discover that at least most of the site is at least 50% comfortable, and yeah, so these are some renders that show the interior character of the building and how the volumes can be inhabited, and then these are
the exterior ones.
Yeah. So, yeah. Thank you.
Thanks, guys. Thank you. Let's jump quickly to feedback. So, because I know Eduardo is about to leave. Eduardo, if you want to share a couple of words.
Good presentation and good work. My initial reaction is I really like the fact that you are trying to integrate the landscape into it, the circulation and the movement. So I perhaps would have actually expanded the research to larger context so that the movement is derived from a bit of a wider understanding of how do you move from one building into the other, not just the boundary, but a bit of outside. And you may realize that your building is actually perhaps 3 buildings that turn around the corner, or just becomes a bit more of a larger context. And then also internally to see how do you move from one box or one ball into the other one. And the optimization teaches you how to read internally those organizations. But other than that, good stuff.
Thank you.
Yeah, thank you. Like we optimize how we move from the one module to another, but like we didn't have time to showcase it for this presentation. So we are sorry for this inconvenience.
I think it was great. Teresa, Emanuele, Theodore, Matilde, who comes next?
Okay, perhaps I can say something. First of all, congratulations for this development. I worked a bit in India, in Hyderabad, with a hotel with SOM many years ago. And we had to carefully study the behavior according to 2 scenarios, monsonic and not monsonic one. I wonder if you can, I wonder why the, let's say, wind has been, or the, let's say, the monsonic scenario has been taken only as a verification scenario, not as a generator of the form. And also in the CFD simulation, I mean, you see trees that are falling apart, but then it's only 4 meters per second as a boundary condition. So it seems that to me that you haven't simulated the most extreme scenario. But okay, I want to hear from you.
No, yeah, I mean, yeah, I agree. Like we didn't simulate the most extreme condition. We like took the generic condition, but yeah, I mean, we wanted to generally understand what is the comfort level in the site. So yeah, so it was more generic in that sense. And yeah, I mean, the simulation, the CFD simulation came in much later into the design process. We wish that, I mean, we could have integrated it earlier, but yeah. It informed the wind actually informed the structural integrity, but not really the the environmental part of it, which came much later. Yeah.
At this point, I would like to thank Eduardo because he has to leave. Thank you, Eduardo, and really great to meet you online. Hope to see you soon in a next version.
Absolutely.
Thanks for your comments.
Good work. Carry on. Thank you.
Yeah, thank you. Thanks. Bye-bye. So yeah, Emanuele, do you want to follow up on that? Or
no,
Teresa?
Congrats on the work.
Perfect.
I'll continue. Thank you for the great presentation. And I think I have an idea why you followed with the CFD simulation in the very end and not at the beginning of the optimization process, since the simulation for the CFD just takes way more time than those numbers, which are easier, like which facade is facing the north and those considerations. So I think I understand why you brought it in to actually evaluate the potential of how to use the open space, but you didn't start from it from the very beginning. One question with a background in architecture, did you also start with like the massing studies with like a concept, or did you just try out which massing performs in the best way based on the criteria you've set?
No, we had a massing concept. I mean, we didn't have time to explain it. So basically, we had three criteria. One is to place the building on the edge because we wanted to increase the retail potential of the site, and then we wanted to shield the site from radiation. So because Mumbai is very hot, and we wanted to shield the southern end, so that was the basic massing criteria that comes into play before we started the optimization. So.
And also the very important aspect that we didn't mention is the noise reduction on our site, which is less of an environmental issue, but more of an artificial anthropological issue. But also this was the important factor for our building enveloping the whole site, because this is very industrial heavy zone of Mumbai with the docks and shipbreaking workshops, which creates the noise level, I think, around 50% over the safe limit.
Yeah.
Thank you for clarification. I think that's a really good reasoning you had at the start, and it would be good if you could mention that as well, because then the environmental performance empowers your design concept, and then it's easier to understand and follow up. Thanks.
Yeah.
Thank you. Yeah, Matilda.
Okay, thanks guys so much. It was really interesting. I just maybe on in terms of design, I see that you've taken your volumes, and basically the larger volumes you've just split them in two with the floor in the middle. And I think that maybe that's something that you could critically reflect upon for future iterations, in the sense that you pick a very particular shape. So maybe it's interesting to understand how to work with that particular shape, not just in an external shape, but rather also in an internal shape. And I see that the different volumes, you have volumes of different sizes and also a dome shape. And it might have been interesting also to look at, and I agree with Eduardo's comment, also reflect upon the circulation within the building, and not just in plan, but also vertically, and understand how you could use that potential optimization to also aggregate these elements within some form of hierarchy, and maybe also associate some of the volumes to circulation, because in the presentation you showed that you have the 3 different scales of volume, but they were all associated to a specific function. So it might have been interesting to play a little bit more and look a little bit more on the design of the interior of the building. And I say this obviously because the rest is quite convincing. So
may I quickly share the screen to clarify because the point is that this part of our presentation was purely the environmental part of the presentation, and we didn't have time to further explain the circulation and to further the circulation in our building and the modules and the actual how the actual building works. So sorry for this.
No, it's not a problem. It's not a problem. It's fantastic then if you've treated it. I would have maybe given it some sort of importance, considering that you have reflected on this.
Yep. So yep. Sorry for this. Like this is the, for example, the circulation that you can clearly see, and the white modules are the circulations parts for the building, and and the modules are aggregated together to create the function clusters. So yeah, this was just a quick and also of course also all the parts for the structural analysis of the building. Yeah, but I'm afraid we don't have much time, so I just wanted to say that like we did work on it too.
We did ask for very specific presentations on the environmental side, because I mean, there's there's other presentations that people will join, but yeah.
Yes, everyone. I think this is a bit late to mention, but I just want to put it out there that most groups have worked on the same project, for the studio project as well. So there is a lot more thought behind the architecture that was presented yesterday.
Yeah.
So this presentation is specifically focused on the environmental aspect.
Well, I'm not sure if
should
there's
have
an
mentioned it before.
if there's an archive of the presentations of previous day, like yesterday, for example, the studios. If there's an archive, people, at least the people who are watching, perhaps on Facebook or like who will watch
Yes,
later.
I think the event is still available on Facebook. I
Yeah,
can,
they can
share the links with Jerry, just
so
in
they
case.
they can go to, and also that everybody who's interested can go there and like see the bigger picture. Yeah. So at this moment, yeah, thank you to everyone also for keeping the time, because it's like, I understand like everybody's time, and especially the juries as well, for giving us feedback is really like precious. So thanks to everyone for giving the opportunity, and also for the students to allow feedback to the rest of the groups, because as we grow in time, then people will have to leave, as Eduardo did. Any more comments for this group before we go to the last one? Okay, so last group, and then we'll share some general words.
Okay, hey everyone, we are group 5. So as Juana mentioned, that most of us are working on the same design project, but I think we are the only group who are not working on the same study project. So yeah, just like a hand up before we start. So first so our project located in Krakow, Poland. One second, please. Yeah. Yeah, so our, okay. So first we looked at why the presentation is moving that fast. Okay, I will give up control Flippy and you can control the presentation. Yeah, because it's moving too fast. So our presentation content starts from the climate conditions and the problems that we are going to address, and the plans configuration analysis and building orientations, preferred scheme daylighting analysis. Number 6 is glazing ratio definition. Number 7 is facade iterations, and number 8, next steps to do. And in the next slide, basically our location is inside Krakow, Poland, and our climate is a warm, humid climate. And basically the summer period is from May to August, and the winter period is from December to January. And in the next slide, we can see our sun diagram, which shows the lowest and highest angles of sun during winter and summer, and the sky dome that shows the solar radiation from different directions, from the lower and the highest angles of sun. And then we check the diffuse solar radiation to check which months are we going to face like high solar radiation or high sun angle radiation for our building. And in the next slide, yeah, and then we start to study the wind direction inside our site from different direction, and the most prevailing wind coming from the west direction. And in the next slide, please. Yeah, next slide. And next slide, please, with that diagram. So after doing that analysis, we decided to focus on our main issues. That first, to maximize daylighting inside our building, which is a residential building in Krakow, Poland, and then to minimize the potential rates that will happen inside the space. And of course, versus that, we will have problems during winter for heating loads. So when we are going to maximize daylighting and openings, we will have issues related to heating loads. So we are going to try to minimize it. And last, to create outdoor spaces. And that is a setup for our model. So for our geometry has a floor area of 750 meters. Number of floors are 6, and built-up area of 4,500. And basically we're using CLT materials and glazing double pane, low EP with transmittance of 6%. And in the next slide. And we also looked for the standards, general standards and specific standards for Poland. So basically we need illuminance, which is around 300 lux, and potential glare should be less than 20% of the floor area. And usually housing units in Poland consumes from 100 to 150 kilowatt hour per meter square. So first we started to focus on the day lighting inside our building. So we started with a very base case that shows the building with 6 floors, and we analyzed the day lighting inside the 3rd floor to check the SDA factor, and here we have 36% SDA factor. And in the next slide, we want to increase that factor, the SDA value. So we introduced an atrium in the middle of the building. So we have now 61.3% of SDA. And then we also wanted to check the ground floor to see what is the effect of the atrium to the least floor with the most with sunlight going through the atrium, and we have here SDA value equal to 43.5%. And then we wanted to do 2 things. First, to create outdoor spaces for people inside the units, and then again to move units to outside to catch more daylighting and have better distribution inside our atrium. So here we have an SDA factor equal to 52%. And in the next slide, we have a comparison between the 3 proposals. The first one without any interventions at atrium or shifting units. So we have SDA factor of 36%. And after adding the courtyard, we have 61.3%. And after that, we have the shifted floor with SDA factor equal to 52%. That's it.
Yeah, so then basically we start looking at different building orientation, and we did kind of like the same analysis at the ground floor, considering that the ground floor is the level that gets less solar access. So we start looking at the east-west orientation, where we get up to a point, and we analyze all the different values as well for the north and south orientation. And then we had a third orientation, which was the east orientation. So in terms of concluding that section, so we compare all the 3 orientation, and we conclude that we wanted to continue forward with the east orientation, which gave us a total SDA of 78% and ASE of 39%. Then after that, we took that preferred scheme and we ran the same data analysis. So we start looking at the different location of floors and units. So we did the analysis for the ground floor and the 3rd level. So we also start defining the habitable and non-habitable distribution of the building. And again, so we ran the same analysis in June, December, and spatial data autonomy as well, the annual sunlight exposure for the ground floor. Then we did the same analysis for the 3rd floor. And at the end, we basically compare the worst case scenario, which was the ground floor for us, and against the option where we didn't have any courtyard. And basically what we get from there, although we know that we pick the option where the values are increased, but we think that we try to take that to the next step and define like the glazing ratio and the facade iterations.
Yes, so the next problem that we wanted to address was energy analysis. So the next slide, we'll see the setup for our analysis. And our first baseline was the fully glazed facade. So on the next slide, we perform energy analysis for the fully glazed facade and looked at the spatial data autonomy as well as the ASA. So looking at the energy balance chart, you can see that in the winter we have quite high heating loads, and it is mostly due to glazing conduction. And in the summer, the cooling loads are not very high, so we are not much concerned about cooling, but we want to reduce the energy loss in the winter. So the next slide will show the heating loads for this 90% glazing ratio. So then we started reducing the amount of glazing, and first we reduced it to 50%. So on the next slide we'll show how the heating loads reduced by 25%.
but at the same time, the daylight autonomy didn't change much, and we reduced ASA for 12%. And our next step was to further reduce the glazing ratio to 30% on the facade, the west, north, and east facade, but we kept 50% on the south to catch more heat gains. And in this case, we further reduced the heating loads by 30%. And then we will show the full analysis for all the whole building. So we were able to reduce the heating loads. And in the next slide, we'll be looking at the energy, the temperature, the surface temperature, and then the energy balance again, to see that we were able to reduce the glazing conduction ratios. So the next thing that we looked at was different. So the conclusion was that we were able to reduce the heating loads, and the daylight autonomy was not very much changed, but what we are still seeing was a lot of direct sunlight. So the next thing we wanted to address was reducing glare, and we tried different facade iteration. So our first iteration, so we started with the glazing ratio from energy analysis, and then we started adding louvers, and we had them in first, we had them both uniformly and very uniformly distributed, and we had also variable distribution of the louvers. And then we tried those 3 different scenarios, one without louvers, then with varying louvers, and with uniform louvers. And on the next slide, we'll show what was the performance of each option. So this would be the first iteration, and we can go through the second and the third, and we will have the comparison slide next. And so then we, looking at the comparison between those 3, we could see that the spatial daylight autonomy was quite high with the first 2 options, but it reduced significantly in the third option. But at the same time, we were able to go down with annual sunlight exposure from 50 to 30%. So we decided to that it was important to reduce this potential of glare with the to reduce the annual sunlight exposure to 30%. And yep, and then so then our next steps, because we thought that we need to reconsider the massing design to control the glare, and then we also would like to have more time to explore different wall ratios and provide maybe a dynamic facade option. And then we also, another area of interest would be to look at the thermal comfort zone for our outdoor spaces and further optimize the building orientation, massing, and whole energy simulation for the building. And this is all. Thank you.
Thank you very much, and thanks for keeping the time. Comments?
If you can stop sharing screen.
Yeah, we will.
I can start.
Yes.
Thank you so much for this very thoughtful analysis, which is run quite in depth. I have a couple of comments. The first is that the building is standing by another building. And I suggest that you run also the lighting analysis of what is happening on the other building, because each act of construction within the city has serious consequences on the surrounding, and you may overshade the other. You change completely the thermal picture for the other building as well as the lighting picture for the surrounding building. The second is that you have a strong emphasis on the cooling loads, but the summer and the new summer, I mean, if you're in Krakow, you know that the latest summer have been very warm. So it's important that you consider or study the summer scenario, polarizing a little bit more. I think your work on that type of that on that scenario. Yeah, so these are the 2 main comments. I don't know if you have any points about that.
Yeah, thank you. But I think we decided to neglect maybe Alexandra, if you want to go, it would be better because
no,
Alexandra is the one from Poland. Yeah, so
yeah. So I think in the weather analysis, the heating loads are the most important. But as I agree completely what you say, that each summer gets hotter and hotter in Krakow. So I think it's very. We also look at the urban heat island effect, but we didn't include it into our in our presentation. So I agree that looking at cooling loads will also be a very important thing.
Yeah, if I can add, first of all, thank you for your presentation. It was a glimpse in sort of like detailed design. I think this project kind of showed this the most. And I like I mean, again, the metrics are completely orthogonal, which really helps when you try to optimize or explore. It gives you some problematic. What I think, my one comment is on, I think, daylighting performance, and from certification projects, which seems to be kind of the approach, the way you approached it, the more like metric-based approach. They do have certain problems in dealing with daylight performance and especially daylight design, specifically because they tend to set targets that, let's say, are not so closely linked to the occupant. So I think like one maybe suggestion that I would have is to consider daylighting as a bit more general, not just the metric or the daylight autonomy, right? But a combination of factors, of views, for example, of glare. And I know you had that, for example, the limit of glare and daylight autonomy. This is what LEED tried to do, for example. They had a minimize glare, increase SDA, right? And find the sweet spot. Of course, no one managed to do that because it's very hard. So like maybe a bit expanded, like, of course, we need to use the metric and it's helpful. But perhaps like curate the metric with a sort of occupant perspective. I think that's kind of important for daylighting. If not, it's quite easy to optimize it. You just maximize autonomy. And and the similarly on the energy performance, and I may have missed that. I'm sorry if I may have missed it. It's nice to think of things a bit, maybe not just consumption, but as Emanuele was saying, like load, and how do you affect the neighborhood around you, and how, so this kind of like, and I think if we do that, even though I haven't tested it extensively yet, but if we do these sort of small changes in the metrics, maybe the scenarios that get created might be more interesting. But I think that, but yeah, it was a glimpse on detailed design. It's only a certain limit of things we can do at that detail, but yeah, just a few ideas on how to approach it. Thank you very much.
Thank you, Theodore. Any more comments on this one?
Just a quick add-on.
Yes.
Thank you for the comprehensive presentation, and I really enjoyed like how you went to steps, because for like from active and solar shading, like how you went from the massing of the building to the very really detailed design of the facade and everything. What I think, because you mentioned this potential next step, like the outdoor thermal comfort, I think if you would do that step before, you would actually influence the massing and the location of the building on the plot, instead of like on the later hand, just using it as a landscape tool, how to place and arrange the outdoor space. But besides that, really nice work. Thank you.
Yeah, that would be perfect.
Yes,
thank you.
Definitely.
Great. So at this point, I think we should thank the jury for being with us, and thank all the students for the really hard and great work, both in amount and also in quality, I think. So congratulations to everyone. Yeah, let's do some like virtual clapping here. And yeah, I'd say two things from my side. One of the biggest points of success, I think, of the studio of the seminar was that it actually informed a lot your actual studio projects, and it was useful. This was like something that was worrying us in the beginning, that maybe we'll go a little bit more technical or a little bit more kind of like scientific, and we would deviate from your project work. But I'm really happy that it actually informed your projects. And I saw yesterday in your studio presentations that you actually kind of like produced work that was really kind of like relevant to the environmental conditions. And also the other point, which was a big bet from our side, which was to focus on the research questions, focus on the science, focus on the actual understanding of the simulations. I'm really happy and very grateful to Aris and Sarah for achieving that, because I think that you did achieve that. Maybe last words from Theodore, Emanuele, and Teresa before they go, and then we can hear from Aris and Sarah. Just a couple of words, each one, if you want to share.
Okay, I'll start.
Yeah, thanks.
First of all, I have to congratulate all the students, because these achievements are amazing in such short time, but also congratulate the teachers because and the leader, because Angelos and Sarah, as well as Aris, have done an amazing body of teaching. I'm really impressed to see this work. How long was the master up to now?
It's I think this is 8 weeks in total. This specific course, the specific.
It can be a year project, so it's amazing. Congratulations to everyone.
Thank you. It means a lot. Theodore,
on my side, I just want to thank everyone for invitation, for showing us your work, and for taking the time to show us the work. I think it was amazing, and I learned a lot, like always. Even though it seems like we're only providing comments, we also kind of learn a lot, and I already have a lot of notes and a lot of ideas. Thank you very much.
Also, big thank you from my side for sharing your insights to your projects, and also for inviting us. And congratulations to the students, but also to the teachers, because I think it's an amazing work you've done within 8 weeks. And I know it's how easy it is to get lost in the tools in this environmental simulation without losing the big picture. And I think you actually brought it to the point that you like stepped back again and you actually compiled it to a really graphically, but also content-wise nice presentation. Thank you very much.
Yeah, I think the big congratulations go also to Aris and Sarah, because they've done most of the things. I've really not done much in this course, but also to Anna, because she organized everything very, very seamlessly, and we're really thankful for your help during this course. You've made everything run very smoothly. So yeah, I'd say a big round of applause for Anna for sure, for her work. Sarah, do you want to share a couple of words?
Yep. Well, first I want to thank all the students. The work was fantastic. I was really impressed by kind of the progress from start to finish, and particularly by how integrated the performance simulation was with design decisions, from how integrated the optimization early on, and how that moved not just from the massing, but then to different stages. I feel that was particularly kind of impressive. I can see how you've taken not just the environmental concepts, but then the quantification of them into integrated really well in the design. So that was amazing. And I want to thank the jury for the fantastic comments as well. It was really good to get your feedback and your thoughts on the design and on the work and how to improve it and how we can take this forward. And obviously, I mean, lastly, Angelos as well for kind of inviting me to be part of the course. I think that was amazing, and for making that work really well. So thank you all. It was great. Thank you for the students, particularly for making that kind of super interesting experience.
Thanks, Sarah. Aris, last words, and then we close.
Yeah. I would also like to personally thank Angelos and the rest of the jurors for their very kind words and remarks. I think that all of those positive comments, both to us as teachers and to the students, they show that there is a very strong foundation built here through this master's course, that even though we are essentially in different parts of the plant, we are able, to deliver this knowledge and expand upon this knowledge using all those fresh ideas that those students have demonstrated today. And for that reason, I would like also to thank those students for doing, for actually not just comprehending those stuff that we taught them, but also taking into the next level and integrating it into their own work. Since each student had its own, since each group had its, a different pathway to achieving similar sustainability goals, they demonstrate different ways of using those tools and adapting those methods into their own personal workflows. So this is very, very essential for you all guys, that you are going to be, the next in the front lines of design wherever you are. And you are going to be building actual buildings and generating a future for people to live in those buildings, in those cities. So this is all very encouraging. And finally, I would also like to thank Oana for coordinating all this through those difficult times of the pandemic and delivering a very smooth experience of distance learning. Thank you all.
Thanks.
Thank you so much, everyone. I think we are
yes.
Making this a very large thank you message for everything. But I just wanted to say that during the last 10 weeks, I think we all went through this amazing learning curve and experience. And I want to also congratulate all the students for the great work. They are halfway through the final presentations. So I think everyone is now a bit more animated to continue and less scared or panicked that probably set in last week.
We truly hope so.
Yes, but I just wanted to say that I think it was an amazing learning curve, and we all learned from each other, students and tutors alike, to prove that this online and distance learning can actually still work just as well or even better as on-site learning. So.
Yeah. So maybe at this moment, like if there's anyone from the students who wants to say anything, because this is about you, not about us. Otherwise, we'll close at least the live Facebook streaming and the recording, and then we can say goodbye to the jury, and then just we'll share a couple of words between us in a more private setting, perhaps. Yeah.
Huge thank you for the knowledge.
Thank you.
Yeah, thank you all. Thank you.
Big thanks.
Great. All right. So bye, Theodore. Bye, Teresa. Bye, Emanuele. Thank you so much for your time. And yeah, let's turn off the live streaming and bye to the rest of the world.
Bye-bye. Thank you.
Yeah.